Understand ಬಂದಿದೆ ಸರ್?
ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್ ಬಂದಿದೆ.
I can enter now through this link now.
You can.
Yeah.
Very good morning to all of you. I heartily welcome all of you on the first day of our international conference on advanced material science and applications. Now I request our head of the department, Professor Jagannath Reddy, to please give the welcome speech.
Hello. Good morning. Yes. Distinguished Chief Guest, respected Principal, participants and colleagues. It gives me great pleasure to extend a warm welcome to all of you on behalf of the organizing committee for the inaugural session of the online international conference on advanced materials and applications being conducted by the Department of Physics in association with IQAC, RAMAIAH of Technology, Bengaluru. On behalf of the organizing committee, I would like to extend a warm welcome to today's chief guest, Professor Anderson Oral Caires, Federal University of Mato Grosso do Sul, Brazil. Sir, we are honored to have you in this conference and we are all eager to listen to your keynote address after this inauguration. It's my pleasure and privilege to welcome our beloved principal, Dr. M.V.R. Naidu, who is the guiding force for all such activities in RI. Welcome you, sir. We are delighted to have you on presiding over today's function. I extend my warm welcome to all the invited speakers and also all the participants for this today's conference. The COVID-19 pandemic has prompted a global shift in meetings and events, many moving from in-person gatherings to more virtual implementation. Online meetings might lack many of the benefits of an in-person conference, such as face-to-face networking, conversations over dinner, random interactions with resource persons of the conference, and fresh perspectives that can come simply from leaving one's place and moving to the new places. But in spite of all these things, researchers are increasingly trying to accept the new virtual reality of scientific gatherings, a trend likely to continue even after the pandemic fades. So in this conference, the agenda covers a wide range of very interesting items, thought-provoking keynote lectures, oral presentations, and poster presentations relating to material science. Serious researchers and scientists from reputed universities and institutions will take us through the fascinating world of material science. So this is an excellent opportunity for the participants to share their ideas and interact with eminent scientists and network with the experts in these domains. Once again, my heartfelt welcome to one and all, and I sincerely hope you will enjoy the next 2 days of technical sessions and presentations. Thank you.
Thank you, sir. Now I request Dr. Ravindra Melwanki to please tell about the conference.
Good morning, all of you. I am Dr. Ravindra Melwanki, convener of this conference. Honorable Chief Guest, respected principal, participants, and colleagues, I would like to express my gratitude and warm welcome to all our invited and featured international and national speakers. All of our speakers are very special and have been selected carefully so that all of you can have variety of topics and benefit from their knowledge. Any conference serves as a platform for sharing research, developing contacts and collaboration and opportunities within the field of a specific subject. The topics in this conference include advanced materials and functional devices, luminescence and applications, nanotechnology, basics to applications, materials theory, computation and design, engineering materials and composite materials, imaging, microscopy, and adaptive optics. It helps to identify current research trends that might be useful for the design and development of innovative functional materials and potential new products. The good response to this conference is evident with more than 310 registered participants. The technical sessions and poster and oral presentations are planned in such a way that to increase the knowledge of the subject and to open the minds of the researcher towards specific research directions. Holding this conference is also an achievement within itself. The conference organizing committee have worked very hard to make this online conference possible. We truly value our participation and support for this conference. Thank you so much for registering and for your kind attention and participation. Because of a large number of participants and due to shortage of time, only few contributed papers could be accepted for the oral presentation. We are sure that this conference will help you better understand and obtain the knowledge necessary to improve the new products. The authors who would like to publish full-length articles can submit the same after the conference from 5th September to 20th September 2020 using the link provided. After the evaluation process, the selected articles will be published in the Journal of Emergent Materials. With your presence, participation and deliberation, I look forward you to a very successful, enjoyable and memorable, rewarding experience. Thank you.
A good day to everyone. I am Dr. S. Vaijayantimala, Assistant Professor, Department of Physics, RAMAIAH Institute of Technology. Take immense pleasure in welcoming you all to our international conference on Advanced Material Science and Applications. It's a great honor for me to introduce and welcome our chief guest for the day, Professor Anderson Cares. Thank you so much, sir, for accepting our invitation in midst of your busy schedule. To introduce himself, to introduce our chief guest is a professor of physics in optics and photonics group, Institute of Physics, Federal University of Mato Grosso do Sul, Brazil. Okay. And about his career details, the professor has done his bachelor's from Federal University of Mato Grosso do Sul. His PhD is from University of Sao Paulo, and he has done his postdoctoral fellowship from University of Sao Paulo, and he is a professor, substitute professor in physics in Estadual University of Mato Grosso. He's adjunct professor in physics in Federal University of Grande do Rio. Sir is holding many positions as a research fellow in Department of Biological Sciences, University of Essex, head of the rector's office, and visiting professor in School of Life Sciences, University of Essex. And our chief guest has got many research grants for the last 10 years, which goes in a list. And he's a referee for many journals. He has guided many research students, and his publications goes in pages. His publication is it's difficult to read all his publications. He has done so many publications. It goes beyond words here. And I'm very happy and thankful to you, sir, for accepting our invitation and joining our international conference today. Over to you, sir. You were invited to deliver your chief guest address here. Thank you, sir.
Good morning to all. Thank you very much for your kind introduction. First, my best wish to our authorities present here. I would like to thank the organizers for the invitation. I also would like to thank and congratulate the RAMAIAH Institute of Technology and our organizer for promoting this event. For me, it's a great pleasure to be part of this conference. I'm very glad to participate in this inaugural section, represent the speakers and all participants in this very important event. One initiative like this, it's very important to help our scientific community to remain strong and motivated to propose new solutions to the nowadays challenges and also to be prepared to the next challenges. Definitely, we are facing the biggest global crisis of the Second World War as a consequence of the coronavirus pandemic. Unfortunately, several families have lost their loved ones despite the great work done by the health workers and key workers from all over the world. Here it's important to stress that several innovative solutions have been proposed and done to help us to overcome the current crisis, in which many solutions are related to the development of new advanced materials and new methodology based in advanced materials. So you need to remember that advanced materials and new materials, new technologies, research involve discovery of fundamental principles of chemistry, math, and physics that can be applied to control the properties of new materials and then fashioning materials or nanostructures for real-life applications. So our scientific community has a crucial role to play in help and improve the daily life of our society. I'm pretty sure that each one of you who are participating in this conference is contributing or is going to contributing to develop or apply advanced materials to solve important problems to our society. So once again, I'd like to thank the organizers and the RAMAIAH Institute of Technology for making this conference possible and for creating one exciting environment for the exchange of experience and learning during this difficult moment. Finally, I wish you good work and a useful conference. Thank you very much.
Thank you, sir. We are very thankful to you. Thanks for the chief guest address. Now, I request our respected Dr. N.V.R. Naidu, Honorable Principal, RAMAIAH Institute of Technology, to please give the presidential address. His audio is... Sir, your audio is not on.
Very good morning to all of you. Could you hear my voice?
Yes, sir.
Yes, sir.
Distinguished chief guest, Professor Anderson, RL Cares, the Federal University, Mato Grosso do Sul from Brazil, Dr. J. Jagannath Reddy, Head of the Department of Physics, Dr. Ravindra, the convener of this conference, and all the registered participants and others. I'm extremely happy to note that the Department of Physics, in association with Internal Quality Assurance Cell of RAMAIAH Institute of Technology, is organizing the first online two-day international conference on advanced material science and applications. And I congratulate the whole team, that is the Professor Jagannath Reddy, the Dr. Ravindra and his team, for taking the initiative and hardworking to conduct this two-day international conference. At this juncture, I would like to brief about our institute. Dr. M.S. RAMAIAH, a philanthropist, founded Gokula Education Foundation in the year 1962 with an objective of serving the society. M.S. RAMAIAH Institute of Technology was established under the Gokula Education Foundation in the year 1962, creating a landmark in technical education in India. M.S. RAMAIAH Institute of Technology is offering 13 undergraduate programs and 15 postgraduate programs. All these programs got accredited by the National Board of Accreditation. The institute is accredited with A grade by the NAC, that is National Assessment and Accreditation Council. Visvesvaraya Technological University, that is our institute is affiliated to the VTU, and the University Grants Commission India have conferred the autonomous status to the MSRIT for both UG and PG until the 2029. The institute has 380 competent faculty, out of which around 60% are the doctorates. All the departments, that is the 18 departments, are recognized as an R&D centers affiliated to the Visvesvaraya Technological University. To promote research culture, the institute has 300 research scholars pursuing PhD, and we established the Center of Excellences in the Imaging Technology, Center of Excellence, Advanced Material Technology, Center of Excellence on Cyber Physical Systems, and Snyder Center of Excellence. Coming to the conference, preparing institutions of higher education to meet the new challenges should be the prime concern of the policy makers. Unluckily for us, the proactive management is keen on introducing a host of strategies for improving the quality education. We endeavor to provide our students with both technical knowledge and developing analytical capabilities so that they are ready to compete and stand out anywhere in the world. RAMAIAH Institute of Technology achieved the 59th rank among the top 1,000 engineering institutions across India and first among the institutions affiliated to Visvesvaraya Technological University, that is VTU, Karnataka, as per the National Institutional Ranking Framework announced by the Minister of Human Resource Development, Government of India for the year 2020. Related to this conference, as I already told, Center for Advanced Materials Characterization and Technology, which is in our premises with the facilities such as X-ray diffractometer, UV visible spectrometer, UTM, TGDTA, spectrofluorimeter, impedance analysis, and many more. The Department of Physics, RAMAIAH Institute of Technology, has been recognized as one of the research centers affiliated to VTU, and they are all well qualified and dedicated faculty members of the department are actively involved in the research. Material science and engineering has played a pivotal role in the development of industrial world and in bringing about the transformation in the society. This present conference covers a wide range of topics on material science, which are really interdisciplinary in nature. I'm very happy to note that they have received more than 300 registered participants in this conference with different research background in the areas of material science, physics, chemistry, and engineering. The authors in this scientific program are unequally placed to share their rich experience, innovation, and research results. I hope that these participants shall be greatly benefited from the invited talks and technical sessions. If you see this, the program, there are 7 technical sessions, out of which 4 resource persons are from abroad, that is University of Poland, University of Qatar, University of Mauritius, and across India, some universities are representing. I wish the organizers all success in conducting the conference, and I also wish all the participants a fruitful academic interaction during the conference. Thank you.
Thank you, sir. Now, distinguished chief guests, respected principal and participants, as a co-convener, it is my privilege to propose the vote of thanks for the inaugural session of the conference organized by the Department of Physics, RIT. On the behalf of the organizing committee, I extend our sincere thanks to Professor Anderson, Federal University of Mato Grosso do Sul, Brazil, for accepting our invitation to be the chief guest for today's function and to deliver the keynote address. Thank you, sir. It's a great pleasure to have you as a resource person in this conference. We are all eager to listen to your technical talk. Our beloved and dynamic principal, Dr. NVR Naidu, is the guiding source for all of such activities in the college. Thank you, sir, for presiding over the function and delivering the presidential address.
Thank you.
We extend our sincere thanks to Chief Executive, Vice Principal, Academic Registrar for their support and well wishes. I also give my thank to Professor Jagannath Reddy, HOD Department of Physics, for his kind support at each and every step of this conference. At any such event would not be successful without the participants. On behalf of the organizing committee, I thank all the registered participants for being with us today. Thank you one and all.
Thank you, Dr. Kalpana. Following our inaugural function, now we will move on to our technical session. It's a great pleasure and privilege to have an opportunity to listen to Professor Anderson Cares. It's a great honor for me to welcome him to deliver his technical talk on enhanced photodynamic action promoted by silver nanoparticles loaded on reduced graphene oxide sheets. Over to you, sir.
Thanks again for the invitation. Let me share the presentation with you. Just a second. Well, thank you again for the invitation. For me, it's a pleasure to be here in this difficult moment. It's a very important initiative as this conference. Today, I'm going to talk how we can enhance the photodynamic action of silver nanoparticles when working together with graphene oxide, okay? I'm from Federal University of Mato Grosso do Sul, and I'm professor in physics in the Institute of Physics. First, just to show that my state, Brazil, is 9.5 hours ahead from India. So the time here, it's around 1 a.m. So I do apologize in advance if my brain does not work well during the presentation, but I try to do my best, okay? Well, Brazil, it's located in South America. Mato Grosso do Sul is one state of Brazil. Brazil is divided in 27 states, and Campo Grande, where is located Federal University of Mato Grosso do Sul, is in the central part of the Mato Grosso do Sul states. Here is one map representative of our institution. At Mato Grosso do Sul, Federal Mato Grosso do Sul University, you can do science at the Physics Institute. We can enjoy the nature. There are a lot of green areas around the campus, and also we can be fun of football because we have a big stadium located in our university, as you can see here in this picture in the left bottom side. The optics and photonic groups are composed by 3 professors in physics, me, Professor Samuel, Professor Bruno, and several students in different levels, and the postdoc as well. We have a wide range of facilities in terms of optical device and spectroscopy. For spectroscopy analysis, different kinds of light source, LEDs, lasers, lamps, spectrometers, and bench equipment as well. I can say that we can divide our research interest in 3 main fields, but it's not limited to those. The analytical methods. Our aim is to develop new optical methodologies, especially in biofuel area, biodiesel. The optical spectroscopy, where we aim to develop and characterize new optical materials and biophotonics, where we use light to interact with biological systems to try to develop new ways to detect disease or even to treat some disease. I'm going to show today the photodynamic therapy. It's one kind of way that you can use light to kill bacteria, for example. Here's my presentation outline. I'm going to start with one general motivation, and then I'm going to show the fundamental concept of photodynamic therapy and how nanoparticles can be used in photodynamic therapy. And then I'm going to show one example of the silver nanoparticles can be used as a photosensitizer, and then how we can improve, enhance the action of photodynamic mechanism of silver nanoparticles. My main motivation is to show that a combination of nanomaterials and light illumination can be useful to combat infectious disease. As you know, a variety of microorganisms can cause disease, virus, bacteria, fungi. But despite the existing vaccines and treatments and antibiotics, there are pathogens able to evade all known therapies. Okay, one example is our current situation. Unfortunately, almost 1 million people died caused by the current crisis with coronavirus. So the question that I'm put here for you is, could a bacteria cause a similar pandemic situation? The answer is yes, it's possible. Just remember that a bacteria was responsible for the most devastating pandemic crisis. 6 centuries ago, a bacteria, Yersinia pestis, was the microorganism that promoted the Black Death pandemic. So it was estimated that more than 7 million people died. So it's possible a bacteria induce one pandemic as well, as the history showed us. And despite the lesson of the history, we are prepared or not to face the next great plague. It could be a new bacteria. Perhaps it could be a multi-drug-resistant bacteria. Nowadays, about 700,000 people die every year for infections caused by multi-drug-resistant bacteria or microorganisms in general. But the projections is showing us that the scenario could be worse in the future. Unless innovative action are taken, there are estimated that antimicrobial multi-drug resistance could rise to 10 million lives each year by 2050. So it's a big challenge for our society to fight against the multi-drug microorganisms. In fact, we are starting to face one era like it was faced during the pre-antibiotic era. So the development of antibiotic was very important to change the way to treat infectious disease. But now, with the arising of multi-drug resistant bacteria, we are starting to bring back similar issues faced during that moment. Based on that, the World Health Organization has indicated one urgent need of developing new antimicrobial medicine and treatments. It's one urgent need for our society to be prepared to combat multi-drug resistant bacteria. Well, the question is, Can new antibiotics win this war? It's just a question of developing new antibiotics. I don't think so, because as you can see here, in the up side, you can see the time when antibiotic was introduced, and here when the antibiotic resistance was identified for those antibiotics. So if you look at the past, I don't think so that the new antibiotics could be the best way to fight against the multi-drug resistant. So it's necessary to propose and develop new alternatives to inactivate multi-drug resistance bacteria to avoid a devastating problem in the future. In this scenario, a promising alternative to combat multi-drug resistant is antimicrobial photodynamic therapy. Antimicrobial photodynamic therapy is based in three is based in the interaction of three entities. One molecule called photosensitizer, the light, and molecular oxygen. These three guys working together can produce reactive oxygen species by the photodynamic action. I'm going to show how the reactive oxygen species can help us in this combat against the multi-drug resistant bacteria or microorganisms in general. The photodynamic action mechanism is based in this simple way mechanism. Here is an energy diagram representing the energy levels of the photosensitizer. Is one dye, for example, that can absorb light in the visible range. When the photosensitizer absorbs the light and the photosensitizer go to the excited state, several pathways could be possible to the photosensitizer goes back to the growth state. But if the excited electron goes to the triplet state, this long life state can allow the photosensitizer to interact with one molecular oxygen to produce singlet oxygen or radicals. Singlet oxygen and radicals are very, very reactive, and when produced inside the cell can oxidize the cell and kill the cell. So using this mechanism, it's possible to inactivate virus, bacteria, fungi, and others, okay? In fact, photodynamic therapy was initially developed to treat cancer cells, but now start to be used to combat infectious disease, okay? It's the simple way to understand how photodynamic therapy can help us. So you need light that is absorbed by the photosensitizer. The photosensitizer transfers the energy to the molecular oxygen or charge the electron to the molecular oxygen to produce reactive species to oxidize the cells and kill the cells. What the advantage of antimicrobial photodynamic therapy when compared with antibiotics? The first advantage is that the same mechanism can be used against different microorganisms. Antibiotics only works against bacteria. So it's one advantage, but the most important thing is that the photodynamic action or photodynamic therapy can kill even multi-drug resistant bacteria in the same way or in the similar way that can kill a sensitive antibiotic bacteria. Why? Because antibiotics act in a very specific site or damage the cell wall, or damage the DNA replication or the membrane. So a small change in the cell, the bacteria, for example, can avoid the drug action. The antimicrobial photodynamic therapy does not target a single site. The photodynamic therapy, the reactive oxygen species and singlet oxygen are produced in a multi-target, in the different sites in the cell, so it's not easy to the bacteria try to avoid this mechanism of action. Until now, APDT neither causes any resistance to developing microbes, nor is affected by existing drug resistance. So it seemed to be a good way to combat multi-drug resistant bacteria. Just to show one example, here we demonstrated that it's possible to inactivate one multi-drug resistant bacteria, MCR1 positive Escherichia coli. This bacteria is resistant to colistin. Colistin is a broad spectrum antibiotic and is called as the last resort. So if the bacteria is resistant to colistin, it's a big problem. Here, in this study, we demonstrate that it's possible to inactivate in a similar way that we inactivate one sensitive strain, okay? Here, it's another example that we used one food colorant as a sensitizer. It's one chlorophyllene derivative. It's a sodium copper chlorophyllene. And this food colorant could be used to inactivate the methicillin-resistant Staph aureus. The MRSA is a big challenge for the public health worldwide. There are a lot of deaths caused by this bacteria. So it's one other example that it's possible to use light, a photosensitizer, to promote the inactivation of a multi-drug resistant bacteria. Here is one timeline to show that the photosensitizer in the use of photosensitizer in antimicrobial photodynamic therapy is not new. It's not new. Okay. As you can be see, I don't think it's the picture is good, but it's not new. But lost attention with the discovery of the antibiotics here. Penicillin was the first antibiotic that was developed, and then the attention to the antibiotics was big, and other ways to combat infection disease or bacteria in this case was not taken in consideration seriously. So, but as you can see here, the attention begins to grow with the emergence of super resistant bacteria. So here start to grow again the interest in the development of new photosensitizer. However, there are several challenges that conventional photosensitizers must overcome to improve the antimicrobial photodynamic therapy. And here I'm suggesting that nanoparticles or nanoparticle-based technologies could help us to overcome some challenges in this field. In fact, nanoparticles can be potentially used to improve the photosensitizer's solubility, the photochemistry, the photophysics, the targeting, but the most used way to use nanoparticles in the antimicrobial photodynamic therapy is as a carriers. As here, load the photosensitizers in the surface of the nanoparticles, or load the nanoparticle with photosensitizers to improve the delivery of the photosensitizers. But the photosensitizers is working to induce the photodynamic action. However, it's possible to use the nanoparticles by themselves as a photosensitizers. I'm going to show here 2 examples. One example is the use of photocatalytic semiconductor nanoparticles that it's largely used to degrade pollutants and to produce energy. It's the same mechanism of action that you can use to produce radicals and kill bacteria. It's one way that nanoparticles can be used by themselves as a photosensitizer. And also, metal nanoparticles can be used. Because visible light can induce surface plasma resonance in the surface of metal nanoparticles, and free electrons can be produced during the surface plasma resonance by the light illumination. So if free electrons can be produced, the free electrons find one molecular oxygen, can produce radicals and can induce the oxidation of the cells and kill the cells. So it's not common, but people start to investigate more about the potential of metal nanoparticles to be used as a photosensitizer. Of course, the surface plasma resonance absorption depends on the shape of the nanoparticles, the metal nanoparticles, and depends on the size of the nanoparticles. So you can tuning the way that you can use metal nanoparticles with photosensitizer, just change the size or the shape. So it's a very powerful way to be a tunable photosensitizer. But this is not possible with the conventional photosensitizer, okay? And are silver nanoparticle good candidates for antimicrobial photodynamic therapy? In my point of view, is silver nanoparticles are good candidates for antimicrobial photodynamic therapy. First, because it's well established that silver by themselves can act as antibactericidal agent, especially due to the fact that silver nanoparticles liberate silver ions, and silver ions are very toxic, can damage the cell membrane, can damage the cell DNA, can kill bacteria. So if you can use silver nanoparticles under illumination, we can get one mode of action to kill bacteria, because as I told you, silver nanoparticle, due to the surface resonance plasma absorption, can also be used as a photosensitizer. So we can get a dual model of kill bacteria by the ions liberation for the silvers and for the photodynamic action that can be induced under light radiation. Well, and how we can improve the photodynamic action of silver nanoparticles? It's possible. Yeah, it's possible. One way is to load silver nanoparticles on graphene oxide, graphene or reduced graphene oxide. It's possible. Why? Because the limitation of silver nanoparticles to produce reactive oxygen species is near to the surface of the nanoparticles, okay? If the one molecular oxygen goes close to the particle surface, one free electron can be transferred to the molecular oxygen and produce radicals. But when silver nanoparticles are loaded on graphene sheet, the graphene may increase the probability of ROS production because the phototransfer electron can migrate to different parts of the sheet prior to find one oxygen to react. Because one, it's not the only one property, but one property of the graphene sheet is to present fast charge transfer. So we can enhance the probability of one electron produced from the one free electron produced from the surface plasma resonance to find one molecular oxygen to react and produce ROS. Okay, is the basic principle behind the use of graphene oxide sheets to enhance the capacity of silver nanoparticles to kill bacteria or other microorganisms by the photodynamic action. So we prepared silver nanoparticles loaded in a reduced graphene oxide sheet. The silver nanoparticles were prepared using the coffee extract, it's a coffee powder in water. And we prepared in different ways, only silver, and two different ways of preparation to load the silver nanoparticles on graphene oxide sheet. One, the silver nanoparticles were prepared first and then mixed with the graphene oxide sheets. And the other ways, the silver nanoparticles were prepared in the presence of graphene oxide sheets, just to check if one way could be better than other. Here is some characterization. I'm not going talk about the details, but just to confirm the chemical composition. Here is the surface plasma resonance absorption in the blue region. The blue brings a wide band here. We determined the ion liberation of the silver nanoparticles to try to understand the toxicity mechanism, and also we determined the ROS production capacity of the prepared materials. And here is the microscopic characterization to see if the nanoparticles were successfully prepared or not, and if the particles were loaded or not in the graphene sheet. It's not easy to see here, but here it's possible to see that here is only the copper grid for the 10 TAM analysis. And here we have the graphene oxide sheets with the silver nanoparticles loaded in the sheets. The black dot is the silver nanoparticles. Here's the threshold of the sheet, and only the grid used to place the samples to perform the measurements. So the silver nanoparticles load in the graphene oxide sheet. And here I'm going to start to show the bioassay results, just to check if the silver nanoparticles also can kill bacteria under light illumination in the dark, and if the graphene oxide can enhance or not the photodynamic action of the silver nanoparticles. Here is the bioassay, the results of bioassay with Staph aureus in the dark. Our results reveal that the silver-based nanoparticles can kill bacteria after 3 hours, but it was not observed significant difference between silver and silver nanoparticles loaded on graphene oxide. And it's not easy to see, but graphene oxide by itself sheets were not toxic for the bacteria as well. Okay, so here is only, as I can say, the chemical effect of ions liberation. So silver nanoparticles alone liberated ions similar to the silver nanoparticles when loaded on graphene oxide sheets. Graphene oxide sheets were not toxic for the bacteria. So it's only the chemical effect. Here, under blue light irradiation, we can see that a fast way to kill bacteria is using light and silver nanoparticles. As you can see here, only silver nanoparticle under blue light irradiation start to kill bacteria after 45 minutes. And when I compare the silver nanoparticles result with the silver nanoparticles loaded on graphene sheet, it was possible also to determine that graphene oxide help silver nanoparticles to improve, to enhance the photodynamic capacity, as a higher photoinactivation was determined for silver nanoparticles loaded on graphene oxide sheets. So in fact, graphene oxide sheets can improve the photodynamic action of silver nanoparticles. I'm going to show in the next slide, but the main idea that I showed a few minutes ago is the fact that the graphene oxide sheet can enhance the probability of the free electron find one molecular oxygen to produce reactive oxygen species. Also, we determined the toxicity mechanism, that the chemical effect, the ions, and the photochemical, the two pathways induced DNA damage in bacteria. So the DNA damage impact the bacterial replication and then can induce the bacteria inactivation. But here is the other microscopy analysis. Here is the control group. As you can see, Staph aureus is a rounded shape, but only photodynamic action, only under light radiation, the silver nanoparticles and silver nanoparticles loaded on graphene oxide can mainly disrupt the cell membrane integrity. So here is a different mechanism that is not, it was not observed only in the dark, okay? Here is just to demonstrate that the initial idea that silver nanoparticles loaded on graphene oxide can have their capacity to produce ROS enhanced. Here is one protocol that we developed to determine the ROS production of silver nanoparticles in the dark here in the first part, in the first 10 minutes. We are measuring the ROS production by using one dye. It's one dye that is not fluorescence, but in the presence of reactive oxygen species, interact with this dye and started to produce fluorescent molecules. So we start in the dark to determine if ROS production are induced by silver nanoparticles in the dark, and then under illumination. As you can see, a fast growth of the fluorescence indicating the production of ROS under illumination. Here is just to show that coffee almost not produced, reactive oxygen species. Graphene oxide sheets were able to produce ROS, but not in an amount enough to kill bacteria. Silver nanoparticles alone in the blue here produce a lot of ROS, and the other two curves are representing the silver nanoparticles loaded on graphene oxide. So using this data, you can fit the data and determine this constant is the ROS constant production, and we demonstrate that silver nanoparticles loaded on graphene oxide sheet have enhanced the capacity of produce ROS. So this data is in agreement with the bioassay results. Okay. Here it's another observation, but I'm not going in the details here, but just to say that we also, in this study, we also determined that only blue light can be used to inactivate bacteria, Staph aureus, okay? Because Staph aureus has one endogenous molecule that can be used as one endogenous photosensitizer to induce the production of ROS. And we demonstrate that the flavins are the main endogenous photosensitizers and not porphyrin as believed. Okay, but I'm not going to show in details. But just to conclude that if we use silver nanoparticles loaded on graphene oxide sheets under blue light illumination, we can get 3 different mechanisms of action to kill bacteria. One is the chemical effect promoted by the ion release, as demonstrated. I didn't told in details, but you determine the ion release as well. The capacity of blue light of kill bacteria due to the presence of endogenous photosensitizer, and under silver nanoparticle under blue light radiation due to the additional way to kill bacteria by producing ROS by photodynamic action that can be enhanced when silver nanoparticles are loaded on graphene oxide sheets. Okay, if you want to see more details, the details are shown in this publication. And finally, I'd like to say that these results are part of a collaborative project that we aim to develop and apply new nanomaterials for applications in health, environment, and energy area. Here I just showed you the one example in the health, but this similar approach using the similar nanomaterials, nanostructure are being used to another fields, okay, in collaboration with University of Essex, Leibniz University, and UC Davis, California. I would like to thank the funding agents, 3 funding agents, CNPq, Fundact, and CAPS, especially CAPS, that are funding this study, and the INOF. Okay, so thank you very much for your attention and consideration. I'm open for questions.
See, anybody is having questions, you can ask now, or you can put it in the chat box. So since there are no questions, I think Professor has made it very clear, even though it is a very early hour in Brazil now, around 3 o'clock in the morning. Sir has taken all the efforts to accept our invitation humbly and present it in an excellent manner. Thank you so much, sir. Besides your busy schedule and early hours of the day, you took the efforts to accept our invitation and have given a very, very informative and very invoking talk in the nanotechnology field. Thank you so much, sir. We are extremely grateful for this. Thanks again, sir. Now over to Dr. B.V. Nagesh, sir.
Thank you, madam. Good morning, participants, chief guests, and speakers. Privileged to introduce Professor Ramaswamy, our second speaker, who is a professor with the Computational Chemistry Group, Department of Chemistry, Faculty of Science, University of Mauritius. He obtained his undergraduate, postgraduate, and doctorate degrees from University of Delhi. He has been visiting professor of University of Johannesburg and King Saud University. Has been a Best Mauritian Scientist Award in 2016. He has many peer-reviewed journal publications to his credit, around 230 publications. He has guided around 60 undergraduate projects and 10 postgraduate projects as well. He has around 11 ongoing and completed doctorate students. He has got around 9 funded projects. Some of them completed, and he has contributed to 9 books. Welcome to Professor Ramaswamy. Welcome you, sir. He is now going to speak on graphite, graphene, silicene. What next? Okay. Over to you, sir. Thank you.
Thank you very much for the kind introduction. I hope that you can hear me properly.
Yes, sir, we can hear you.
Thank you very much, madam. So very good morning to everyone. Most probably good afternoon to some of you. I hope not good evening. Right. So it's my pleasure to join with you today for this excellent initiative of having an online seminar conference in view of the travel restrictions that we are having in the world. It has been my pleasure to accept the invitation from Dr. Ravindra, who contacted me. And today, the title of my talk is Graphite, Graphene, Silicene. It's not a mistake that ... but it's on purpose. And then what is next? So I am myself Ponadurai Ramasamy from the University of Mauritius. I am also a visiting professor with the University of Johannesburg and a professor extraordinarius with the University of South Africa, the last 2 universities from South Africa. I always like to give this slide, share this slide whenever I give a talk, because some people, they do not know where is Mauritius. And so Mauritius is a very small island in the Indian Ocean, right? And most probably you'll need a lens to see Mauritius. But then so many people, they confuse it with Mauritania or Malaysia. But now with the internet Google issue, it's very easy to go and check for Mauritius. But I always like also, I've given several talks in like online where there were participants from India. And I think this is a very nice slide, which gives a comparison between Mauritius and in India. So if we see in terms of kilometers square, so Mauritius is about 2,000 kilometers square. And of course, you can realize the size comparison with respect to Mauritius and India, which is almost, to my understanding now, almost 1,500 times larger. And when we talk in terms of the population, so Mauritius is about 1.3 million, whereas we are talking about 1.35 billion in India. So this gives you a comparison for your own understanding about the two countries, Mauritius and India. Now, let me come back to Mauritius before I really start with the scientific talk. It's always good to share with you something about Mauritius. Well, Mauritius is quite, I should say, famous for the sun, the sand, and of course, the beach. But unfortunately now, due to travel restrictions, it's difficult to go for the travel. I hope that everything will be settled soon and everyone will be able to live the normal life that we had previously. But for anything, we have to adapt to the change. Now, this is the Le Mans mountain. So, and when it is the Le Mans mountain, right? So you realize that this is a type of UNESCO recognized mountain. So why it is recognized by UNESCO? Because basically the history associated is that there were slaves who came to Mauritius from different parts of the world. They went on to the mountain to hide their masters, but when their masters came, they jumped to death. So this is the history associated with it. And this is the same mountain from a different view. And this is a dormant, dead volcano, Trosef, but so many scientists saying that this is a dormant one. I hope it's really dead and it's not dormant, because if it is dormant, the day that it will erupt, Mauritius will no more be there. The next now go to the University of Mauritius. Now, you may realize that when you compare, India with Mauritius, Mauritius has only like now, let's say 4 or 5 public universities. Of course, there are many private universities. At one time, there was only the University of Mauritius as the government-owned university, but now there are some 5 of them. So this is the building which was there at the starting of the university in the 1950s. So you may realize that at that time research was concentrated only for sugarcane because Mauritius agriculture, because Mauritius was dependent on sugarcane at that time, although now the dependence is less. With time, now we have a full-fledged university with different faculties, and at the Department of Chemistry, we have about 300 students from the undergraduate to the PhD level, and there are 10 academic staff involved. Myself now, I lead the computational chemistry group, and we have our own computational chemistry laboratory. I may share with you that when I joined the university in the year 2000, there was no computational chemistry being offered at the university here. I introduced the subject at teaching level. I've been able to take it, scale it up to the research level. And now I should say that after so many years, things are going on smoothly. And you may realize that in this type of laboratory, you will not be having any chemicals, but you will be having only computers. But then these computers that you can see over here, they are only the access to a supercomputer where we do the computations. And at the back, you can see a picture of Erwin Schrödinger, who happens to be the one behind the famous Schrödinger equation, which is the fundamental of computational chemistry. Now, if you allow me, in terms of a history associated, so we started in 2000, in the year 2000. Then in 2003, we had the module at the undergraduate level. I had only one MPhil PhD student. Things have really scaled up over the years. And I'm pleased to say that in 2020, the group consists of one postdoctoral fellow, 2 research assistants, 8 MPhil PhD students, and then MSc students and BSc students. MSc is for postgraduate and BSc is for undergraduate. And we have reached almost 230 publications. Now, with this brief introduction, now I will go to the scientific part of my talk. And today I will be focusing about computational chemistry, nanoscience and nanotechnology, of course, our research, our future plans, and I will summarize. Don't forget that I will try to orient all these to graphite, graphene, silicene, and what will be next. Now, you should not forget that chemistry is one of the science subjects. So if chemistry is one of the science subjects, it should remain experimental. You cannot do science without doing experiments. But then you will find that computational chemistry becomes a useful tool. Now, this is the equation which really makes many people afraid. Many students, they really turn away from physical chemistry or quantum chemistry or ultimately computational chemistry because they don't like this equation. But if you really sit down and think, this is the fundamental of quantum chemistry. And I hope that you can still recall that this equation can be solved only for one electron system. And if you go to 2 electron system or larger number of electrons, unfortunately, you cannot solve this equation exactly. When this is not possible, scientists have devised means and ways to solve it approximately using numerical methods. These methods, they have been known for long. And now these methods are implemented using codes in chemistry. And here we are, computational chemistry. So if you have to summarize what is computational chemistry, basically it uses numerical methods to solve the equations in quantum chemistry numerically, basically to obtain the electronic energy. And of course, there are other derived parameters. Now, having known about computational chemistry, definitely there are some advantages in the sense that it really fits to the whole concept of green chemistry, except of course that you have lots of electronic waste that you dump around, and there should be means and ways for controlling this. No doubt you will realize, or you might be knowing, that computational chemistry have different applications. So the first one is electronic structures of the existing and novel molecules, complexes, and clusters. Thermodynamics and spectroscopic kinetic parameters of molecular species. Global warming potential, global warming species and their reactions in the atmosphere. Cycloaddition and nucleophilic reactions. Solar dyes and their efficiencies. Drugs and their applications. Interdisciplinary fields such as astrochemistry and biochemistry. But today, although I did not mention it among the applications, now you'll realize that there are interdisciplinary actions where computational chemistry has been used. And the field has developed to such an extent that it is now like a firm science. And you really see that you have Nobel Prizes even being awarded. So in 2013, the Nobel Prize in Chemistry was awarded to 3 professors for the development of multi-scales model for complex chemical reactions. We should not forget that in 1998, the Nobel Prize was awarded to Professor Kohn and Professor Popov for development of density functional theory, and of course to Professor Popov for development of computational methods in quantum chemistry. Now, in parallel to chemistry, in parallel to science, now there is a fancy word around, namely nanoscience. But the question is, what is nanoscience? It's a Greek word coming from dwarf, and the study and manufacture of extremely small particle. You see, this is something which is non-scientific. If I tell you that something is small, something is big, something is large, there should be a reference. I can give you an interesting example that makes you realize the whole thing. There is a common question, for example, for the students. Why is aluminum used for the construction of the body frame of aircraft? A very common answer is aluminum is light. You see, although the idea might be correct, but the word used is wrong, in the sense that, are you telling me that an aircraft is light? So you have to be very careful in terms of the word that you use. Most probably in science, if you really have to give a scientific answer, the best answer will be aluminum has a low density. Aluminum has low density and aluminum is light. These are completely different things. Now, when I'm talking about nanoscience, small, I should have a scale. So then only I can say what is small, what is large. So here's the scale. So what you can have as the macro scale, what you can have as the micro scale, and what you can have as the nano scale. So the nano is of the order of 10 to the power of 9 meter. And there are many things that falls under the nanoscale. For example, the cellulose nanofibrils, the DNA, even the hydrogen atom. What about micro? Whatever, for example, the hair. What? The design, characterization, and production and application of structures and devices and systems by controlling shape and size at nanometer scale. And you will realize that the nanoscience and the nanotechnology, it is taking inputs from chemistry, biology, physics, engineering, and now you can see that other fields are getting into medicine, biotechnology, material science, information technology. Now, of course, with the nanotechnology developing, with computational methods developing, now you have computational nanotechnology. Now, what is computational nanotechnology? Allow me to read. Computational nanotechnology is a branch of nanotechnology concerned with the development and use of computer-based models for understanding, analyzing, and predicting the behavioral properties relevant to nanotechnology. You might be surprised to know that computational methods now, you can have fields such as computational nanotechnology, computational medicine, computational chemistry, computational physics, computational biology. Do you know that we have computational arts? We have computational journalism, and we have now something which has already been coined is computational thinking. You have to think in a now when you wake up in the morning, you need to have some computational thinking. What should be the first thing I do? And like many of us now are very busy, so there should be a priorities in terms of the work that we might be doing today. And there are things that we need to postpone for other days. But then I always like to relate it to the operating system. Basically, most of us, we are using Windows as the operating system, and some of us are using Linux as the operating system. I always like to make a comparison between our brain and these operating systems, in the sense that Windows operating system usually process one thing at a time, but then with Linux, you can process many things at a time. And have you ever tried, just try to, for example, read something, and at the same time you think of something else. You'll realize that you will do mistake either in the reading, because your brain cannot process two things at a time. Unfortunately, our brain to date can process only one thing at a time in the processing. So who knows now that research is required. How nice it would have been for me to give this talk, and at the same time I see myself relaxing on the beach and then doing some relaxing mind, but you can't do this. Either you concentrate and give your talk, or you relax yourself and forget about everything. Your brain cannot do two things at a time. Now, I have some literature with you to share about computational nanotechnology and what might be the importance. Right. Now, we have sustainable nanotechnology, opportunities and challenges for theoretical and computational studies. Allow me to read. To help better to understand sophisticated experimental measurements and ultimately guide the design of new experimental investigations, it is essential to conduct theoretical and computational studies on the nano-bio interface. You have other papers, for example, large tunable image charge effects in single molecule junctions, an extended defect in graphene as a metallic wire, the surface science of nanocrystals. These and other computational techniques aid interpretation of experimental data and propose new directions for experiments. Another paper, how can ab initio simulations address risk in nanotechnology? Another one, intelligent computational nanotechnology, the role of computational intelligence in the development of nanoscience and nanotechnology. As you may realize that these are papers that were there from at the start of the whole concept. Of course, you can update yourself with respect to literature and then understand. But you'll realize that in the whole process, there should be a cross-fertilization between experiment and theory. If both of them work together, you will see that things can go faster. But then what is next? Now, next in the field I don't know whether you have really thought or realized now we are no more talking about nanoparticles. We are no more talking about nanoscience, no more about nanotechnology, but now we have picotechnology. We have picoscience. Now, what is nano? What is pico? So now we go further down to 10 to the power minus 12. And there are some interesting papers which appeared when the whole science came into picture about going to the pico scale. I will not go into the detail of this, but I leave it to you to really give it a good thought. Now, having talked about, having talked about chemistry, having talked about computational chemistry, having mentioned about computational nanotechnology, I can't just come here to give you an overview of what others have done. It's always good to share about the research that are being developed in the group. And I will share with you our research direction. And I like this whole idea from graphite to graphene, silicene, and most probably give it a good thinking. What is next? Now, I'll share with you one research related to the functionalization of fullerene and graphene. Now, this is your nice, allow me to take some water, please. Thank you. So, this is our famous buckyball with respect to the fullerene structure, which was the Nobel Prize was awarded to 3 professors, and I'm pleased to share with you that I've interacted with Professor Curl and even Professor Croto in my scientific career, and they are real nice gentlemen who will really share scientific thoughts with you. And now come to the whole story. We all from basics, right? We all from basics, right? Know about using pencils, using the lead in pencils. So I will not go into the detail, but I hope that everyone knows about graphite. So why do you have your, let us suppose, your pencil? You have graphite for the simple reason that now it will be slippery. It will leave that black carbon on your white paper. And students, they learn at the second, in the lower level, why graphite is slippery because of the weak forces between the between the layers. And of course, you can't use diamond for writing up because it is hard, and so on and so on. Now, it's so beautiful. It's so beautiful. If you allow me just to get a, if we can get, well, I did not get a book, but then if you realize that you have graphite made up of layers, what is graphene? Very simple. Just take one layer from graphite and you will get graphene. So you can realize your copybook. Allow me to take this one. If we take, for example, such a material, of course, this is on a larger scale. So you'll have it 1 layer, 2 layer, 3 layer, 4 layer, and so on, and so on, and so on. So basically, for me, this is graphite. And if we are able to get a single layer of atoms, here we are for graphene. It looks very funny, it looks very interesting. And the 2 gentlemen who basically discovered graphene from the University of Manchester. Again, I do not know them personally, but I had some interactions with them while we were having some research going on. So there should not be any excuse now why you can't really picture what is graphite and what is graphene. And of course, the Nobel Prize was awarded in 2010 to them. Now, we do have graphene, and we do have all other types of carbon single atom scale being joined in a Bucky form and other forms. But then you'll find that they have special characteristics, and they are widely used in, let's say, the concept of hydrogenation, the fluorination, organometallic chemistry, and organic chemistry. And here, you'll find that computational chemistry can really help in trying to understand some concepts at molecular level before you actually go on to the experimental scale. One of them is the cycloaddition reaction. Go down to the Diels-Alder reaction. Go further to the 1,3 dipolar cycloaddition reaction. We know about the 1,3 dipolar, where you have an alkene joining to a diene, and the 1,3 concept, where this is a real simulation. Now, what do I mean by a real simulation? Most probably, for those who know a bit about computational chemistry, I will tell you how this simulation has been obtained, and you can give it a good thought. I can tell you, if you give this idea to maybe someone having a good knowledge of programming, a good knowledge of video mounting, I think it should not be difficult for him to have 2 black balls, 4 white balls, and so on to make them join to have a movie. I don't think this is difficult, because if they are doing Bollywood movies using computers, I don't think that this simple simulation will be different. But my dear participants, allow me to tell you that this is not at all a computer man-made thing. This is generated from the computation. Now, what I mean by the computation, whenever you're adding the alkene to the diene, it has a transition state. And when you have the transition state, it is possible to model the transition state precisely. And using the intrinsic reaction coordinate, you are able to simulate exactly how the alkene joins to the diene. Now, if you try to see it properly, allow me to explain to you what are the possibilities. It is possible that both the carbon of the alkene join simultaneously to the diene down. This will be a synchronous cycloaddition. Or it may be that one joins and the other one takes a longer time to join, and this will be asynchronous. So both of them will join to the equal extent. One of them will join, the other one will take longer time to join. You can visualize this, you can predict this at a computational level without any interference of additional factors. Now, this is the basic that I explained, where you have a dipole adding to a dipole aerophile, and of course you get the product. Of course, there are so many studies which have been done on this from a computational point and then investigated from an experiment. But then what we did was we considered cycloaddition to 60. As you realize that as the number of carbon increases, it becomes a bit tricky for the calculation, right? And we have been able to have functionalized graphene. And of course, if you really try to go a bit in the understanding, there are different possibilities of adding the two cyclo addition reactions that you are considering. Either you add to the 6-6 bond or you add to the 5-6 bond. Ultimately, you will have several possibilities in the cycloadditions, and we try to study all these, ultimately come up with a conclusion that if you have fluorine being there, right, it leads to an exceptional result that is to be explored, of course, then by experimentalists. We published this quite a long way back, but then it's still being investigated by experimentalists in trying to synthesize these compounds, in particular the fluorine one. In the same direction, you'll find that there has been a computational assessment of the 1,3 dipolar to graphene. But then you can realize that it's very important that when you're having graphene, since you have an extended sheet, to start having models. So the model classified as 0 by 0, 1 by 1, and so on and so on. So we did this investigation, and we are still doing to see what will be the suitable position of addition, and ultimately what should be the size of the plane system of carbons that we should use to really achieve the result that we expect to have for one sheet of the graphene. So again, this is an example now of an asynchronous cycloaddition. You can see precisely that the carbon is joining first and then the oxygen joins later, right? Now, we have other examples also, and we are really looking at it. Now, I've talked about graphite, I've talked about graphene. Remember that I said that I'll be talking about silicene, and I'll be talking about what is next. Now, okay, we all know about graphene. If you see the press release and so on, the miracle material that could revolutionize our world. But then graphene has several applications: batteries, composites, high performance sensors, and so on and so on. Okay, very good, very good. But then remember that we are chemists and sky is the limit. Being scientists, sky is the limit, and let us think further. Well, okay, carbon is in group 4. The next element, which is just below carbon, is silicon. But why is it that we focus only on carbon and we forget about silicon? I'm pleased to say that now we also have, and we know that silicon is being widely used in the silicon industry. For example, I know myself that we were I recall back a very simple question in the secondary level. What is a conductor? I'm not talking about the one in the bus or whatever. I'm talking about science. So what is a conductor? A conductor is one which will conduct electricity by movement of free electrons, and there is no chemical change. Now, what are examples? All metals. What is the only non-metal? Carbon in the form of graphite. But then I recall that my teacher, he explained that silicon is a non-metal, it is a semiconductor, it is widely used in the silicon industry, in the electronic industry. But you know, this is quite long way back. Now, we have the silicon analog of graphene, which is silicene. But the interesting thing is that it is not planar. It is non-planar. And I may share with you that the silicene term was studied and coined by my good friend, Professor Liu Yan Vun. And basically, he visited my lab. He was here for almost 3 months, right? And I had a team group working on the silicene, and we did some calculation. And this is what I'll be taking today about what is next. Well, as I said, we had carbon to silicon, but then we had the silicon, silicene being coined and so on and so on. But we want to think further. Now, what is further? Now, why not try to move from the carbon, going to the silicon, going to other elements down the group? Why not now how, for example, the borofin, which is just aside to the carbon, why not have, for example, the aluminine, which is another one? And if you go further, why not have the indiene as other novel materials? So this is basically the directions that our research is now focused. From carbon, go down to silicon, go down to germanium, indium, and go sideways to boron, and go further to aluminum. So this is the next that I wanted to share with you. And we have computations going on, and we intend to have the results further. So boron, aluminum, gallium, indium, thallium, and then having carbon, silicon, germanium, and so on and so on. Now, apart from these fundamental aspects, we have also contributed to experimentalists in their quest of using the 2D materials, in the quest of using nanomaterials. I'll just share two with you. One of them is in the water pollution, where we fit to the SDG goal number 6, where now it is known that chemistry can help for the treatment of wastewater by biodegradation, ozonation, electrosorption, and adsorption, and nanoparticles can be useful. Now, we have contributed to one experimental group where they have studied the adsorption of pyridine on silica, and we contributed to their experimental research. I'll not go into the detail. And we also have one application where we have used the expanded graphite electrode with some zinc oxide for the removal of for nitrophenol. Of course, you can check these papers. I will not go into the detail unless we have some additional time. Now, to summarize, I've given to you an idea about computational chemistry, computational nanotechnology. I've taken it in the direction graphite, graphene, silicene, and of course, what may be next. And of course, I've shared with you with our research. Our future objectives, to more collaboration with experimentalists and the industry, more of applied research, particularly what the country needs, and more of communication with the public. You are invited to discuss with us for possibilities of collaboration, and you have our email address for contacting us. For those who would like to collaborate with us, there is a good website, Advance Africa which gives possibilities for travel grants. But now it seems that the whole concept of travel grant have to be changed to online grants for you to be interacting online with us. Of course, I can't just give a talk without acknowledgement. I should give my acknowledgement to the organizing committee of this seminar that we are having today. I should thank the University of Mauritius, the University of Johannesburg, the Tertiary Education Commission, the Mauritius Research Council, the Grid Chem for all computing facilities, and of course, the Computational Chemistry Group. No doubt, I should thank all of you for your patience and your kind understanding in my presentation. I'm very sorry if I've been long and maybe at some time boring, but I'd like to thank you and I'd like to take your questions if you have.
Thank you so much, sir. It's indeed a very, very informative and very good talk. It was not at all boring. You made it extremely clear. You made it extremely clear, sir, with all the travel grant facilities and all those things. You just took us a tour on Mauritius also. Before we started, we came to know about the university history, everything. Thank you so much for such an informative talk, sir. It looks like we have visited Mauritius and attended your talk in person. Thank you so much. Now the lecture is open.
Good.
How? Thank you so much, sir. Now the lecture is open for discussion. Any questions you can please ask. Unmute yourself and ask. So if you want to have some questions, you can put it in the chat box as well.
Yes, so now the question is, I have one question that I can see here. Is silicene better than graphene with respect to the applications? Yes, it's a good question because like I said, the only thing is that graphene is planar, whereas silicene is non-planar. So as it is then, they have properties which are in common, but they also have properties which are not common and might be specific for each of these silicene or graphene and can be used specifically. But allow me to let you know that, for example, the properties silicene, it has not been obtained like an experimentally yet, only the theory has contributed to the understanding of its non-planar, and therefore as the experimental developed towards its synthesis or its availability, maybe there will be more research targeted towards its application. I hope I've answered that question.
Thank you so much, sir. That made it very clear. So since there is no more question, we will thank Professor once again. Thank you so much, sir, for accepting our invitation and giving a very, very informative talk in a very excellent way. Thank you so much, Professor.
Thank you very much. It has been my pleasure joining you.
Yeah, thank you, sir. Now we will move on to the next technical talk. Over to Ms. Gopika.
Good morning. Thank you for being here this morning. Today, we are pleased to welcome Professor K.Y. Rajpuri from Shivaji University. Sir has obtained his MSc and PhD in solid-state physics from Shivaji University. His area of interest includes thin films, solar cells, transparent conductive oxides, photoelectrochemistry, photoelectrocatalysis of water, gas sensor, and multiferrox. Today, he will be talking about thin film preparation by economic chemical method. Sir has guided around 14 PhD students and several MSc projects. He has published more than 180 journals. He has completed several research projects sponsored by DRDO, DST, UGC, CSIR. He has published various book chapters. Sir has patent on iron oxide nanoflakes and nanostructure of zinc oxide for water impurities. He is a member of various research committees and university committees. With that, I ask that you give your full attention to Doctor and help me in welcoming him. Over to you, sir.
Thank you very much for your introduction, and I welcome all of you, and I have wish all of you a good morning in this today online international conference on advanced material science and applications being organized by the Department of Physics of RAMAIAH Institute of Technology, Bengaluru. Before I begin my talk, I would like to thank the organizers, especially convener Dr. Melavanki and head of the Department of Physics, Professor Jagannath Reddy. Also, the principal of the college, Dr. Naidu, chief guest, Professor Kairis, and just now we listened to a very enthusiastic talk by Professor Ramasamy from Mauritius. So I thank organizers for giving me this opportunity to talk in front of you. As in the program, it has been listed, the topic of my presentation is a very simple title, the thin film preparation by economic chemical methods. This talk, though it is not targeted to share with you all what are the current happenings in the research in which I am working, but this is the very informative and very encouraging talk to the newcomers who have begun their research career in the material science. So title of the talk is Thin Film Preparation by Economic Chemical Methods. I am working as head of the department at University Science Instrumentation Center, Common Facility Center at Shivaji University, Kolhapur. In addition to this, I am coordinating the Sophisticated Analytical Instrumentation Facility, that is SAIP Center of Shivaji University, Kolhapur. As you all might be knowing, Shivaji University, Kolhapur has situated in the east-south corner of Maharashtra. It is on the border of Karnataka. Since last 25 years of my research career in the material science, I have been working both on bulk materials and thin film materials. And the research fields in which I am working is the porous ultra-high silica aerosols, composite oxide magnetic materials, chalcogenide thin films, transparent conducting oxide thin films, and all these materials, they are being prepared, synthesized with very economical, cheap, simple chemical techniques. And these materials, they are used for energy harvesting, conversion, and storage devices. And these are used in the solar cell application, gas sensor application, in catalysis, photodetector, and memory registers. As all we know, the materials is a very broad and vital field of knowledge, and it has been the foundation stone of modern technological society. And as all of you know, this material science is the interdisciplinary field in which the various subjects like physics, chemistry, biology, computational engineering, civil engineering, chemical engineering, electronics engineering, and many more, they are simultaneously existing in the research. We know materials, they can be natural or human made. The natural materials, they are like wood, or the human made materials, they are like plastic. Until now, to the mankind, more than 3 lakh different materials are known. And out of these, many are extensively studied, investigated. Here I am giving you the representative list in which the extensive research is being carried out. You can suppose these are as the hot materials: magnetic materials, superconducting materials, thermoelectric materials, supercapacitor, energy devices, electronic materials, biomaterials, semiconductors, graphene, polymers, composites, nanomaterials, and optical and photonic materials. So far as the emerging trends in the research in material science is concerned, there are many emerging trends. Here I am listing few. For example, transparent and transparent and very light porous silica aerosols, conducting polymers. Just now we listened to one of the forms of the top of the carbon. So fullerene, thin film devices, 3D printing, nanoscale machining, titanium aerospace industry, perovskite solar cell. So of these, thin film device technology is attracting great attention due to various applications of these devices and the gadgets made with the thin film technology in the modern age science and technology. We are working on thin film materials in our electrochemical materials laboratory in the Department of Physics of University Kolhapur, and we are investigating various applications such as we are using them as the transparent conducting oxides in the solar cells. We are using them to detect the ultraviolet radiations, chemical gas sensors, in the memory registers. Memory registers we are using, in photocatalysis also we are using. So before proceeding, we define a thin film. This is a very primary thing to all of you, but for those who have recently started their career in the material science research, this thin film has to be precisely defined. So how thin this thin film is? We know the thickness of the acrylic board or the brass board is in the order of 1 millimeter or 1000 micrometer. If you think of the thickness of aluminum or gold foil, the thickness is around 1 micrometer. Anything which is below 1 micrometer is called as thin film. So we can generally define a thin film as a material which is extended in 2 dimensions and which is restricted along the 3rd dimension. And this thin film field has achieved a technological breakthrough in various areas like recording media, semiconductor devices, light emitting diodes, optical coatings, hard coatings, energy generation, storage and conversion, and even in pharmaceuticals, these thin films, they have proved their crucial role. When we think of preparing these materials in thin film form, we can broadly classify the methods through which these thin films can be prepared. They can be physical methods and they can be chemical methods. And the physical method, as we know, they are vacuum evaporation and sputtering. This vacuum evaporation consists of resistivating, flash evaporation, electron beam evaporation, arc evaporation, RF heating, etc. And this sputtering, DC, triode, gator, RF, magnetron, AC sputtering, etc. Gas phase chemical technique, they are chemical vapor deposition particularly, and the liquid phase chemical deposition methods, they are electric deposition, chemical bath deposition, sealer, spray, sol gel, spin, and hydrothermal. So in this lecture, I am going to explain a bit working principle and some of my results based upon these liquid phase chemical thin film deposition methods. So, as I said, physical methods, they are based on the fact that a material in this solid form is converted into liquid form, is again converted into vapor form, and is again condensed in the solid form. So, physical form of the matter is being changed, and solid to liquid, liquid to gas, gas to solid. So, this happens in case of the physical methods, both in vacuum evaporation and sputtering. The film quality of the films prepared with these physical methods is excellent. We have greatest control over the film thickness, the stoichiometry, uniformity, adherence, and whatnot. So these are industrial quality thin films that we can prepare with the help of vacuum evaporation and sputtering. Many devices and gadgets, they are formed with the help of the film prepared with this technique. But one of the disadvantages of this technique is that these methods, they are time consuming methods. They are very costly. They require vacuum. And we know for generation of a vacuum, it requires a large time. In many methods, high temperature requirements are there. And the cooling system also is necessary in this. And therefore, owing to these disadvantages, ultimately one thinks of an alternative method for preparation of a thin films. And ultimately, the chemical methods, they is the suitable answer for this. But in the chemical method, the gas phase method like chemical vapor deposition works on the principle that the initial ingredients, they are taken in the form of gaseous ingredients and they are passed over the heated substrate, and pyrolytic decomposition occurs, and you get a very nice and very uniform and adherent thin films. But here, the disadvantage is when these are not environmentally friendly, and also the high temperature requirement, the temperature of the order of say 800 degrees centigrade to 1000 degrees centigrade. So this becomes, these are the disadvantages of these gas phase chemical methods. But the chemical methods, which are liquid phase chemical methods, namely chemical bar deposition, CBD, spin coating, deep coating, spray coating, sealer, hydrothermal, and electrodeposition, and other. So these are the methods which are very simple. They are economical, they are cost effective, they are not time consuming, and the quality of the film, the quality of the deposits prepared with these liquid phase chemical methods is comparable in even better than the quality of the physical methods. So let us begin one by one these methods. What I will do, I will introduce the method one by one, and I will tell few advantages, and I will demonstrate in front of you the results which are being carried out, or which we have got in our lab. So first one is the electro deposition. So with the help of electricity, we get deposition. So we know electro deposition is the in situ metal coating, for example, where the electrolyte is conducting and we pass a current through this. And in this process, solid material from molecule anions, it gets deposited on the electrode. The main components of the electro deposition method, they are electrolyte. The chemicals of the compound to be deposited are dissolved in the aqueous or non-aqueous electrolytes, solution solvent, sorry. We have substrate, we have counter electrode, and we have power supply. In many cases, they have one more component added called as reference electrode. So this reference electrode is used for measuring the voltage of the working electrode. So we know the cation and anion, they are attracted due to application of a bias towards anode and cathode respectively. And if there is a charge transfer reaction, they get deposited themselves on the electrode. And this deposition is governed by the very well-known Faraday's laws of electrolysis. We know there are two laws of Faraday's. First law states that the amount of material deposited on the electrode is directly proportional to the amount of electricity passed through it. And the second law states that if same amount of electricity is passed through the different electrolyte, then the amount of material deposited on the respective electrodes is directly proportional to their electrochemical equivalents. So this is the schematic diagram of the electro deposition setup, where I have shown working electrode, counter electrode, reference electrode, electrolyte, and the potentiostat, the means to give the electricity or the current. And we know this potentiostat, sorry, something is happening, some arrows, some host is somebody is doing. So electrolyte, it should be conductive as we know, and these electrolytes, they contain suitable metal salt, and these metal salt are being dissolved in the aqueous or non-aqueous solvents. The three electrodes, they are cathode, anode, and reference electrode. Cathode, they are working electrodes or our substrates, and the anode is the counter electrode, which should be inert metallic electrode. And reference electrode is the electrode which is a standard electrode like NHE or SE or AgAgCl. So with reference to which we measure the potentials. So we can apply the bias between anode and cathode potentiostatically or galvanostatically. So we can have the deposition at constant voltage or at constant current. We can have the potentiodynamic mode as well. So for your reference, I have given you the photograph of the thin films of cadmium sulfide prepared via electrodeposition and chemical path deposition, just for your reference. So how it happens? We know when a metal or the chemical containing the metal ions, they are dissolved in an appropriate solvent, then these metal ions, they react or they reduces uh, at the surface of the substrate and they get deposited on the substrate. If more than one metal ions they are present, then they can individually reduce and they get deposited individually, or they can co reduce, they simultaneously reduce and they get simultaneously deposited on the substrate. For example, for the deposition of cadmium sulfide, cadmium 2 plus and sulfur 2 plus or sulfur 2 minus, both the ions they get reduced at the surface of the F2O, which is conducting uh, electrode, which is on glass, and we have a deposition of cadmium sulfide. So one of the disadvantage of this method is the electrodes, they should be conducting. If the electrodes are not conducting, then we cannot have the deposition. In the electrodeposition method, the important parameter is the equilibrium potential, the potential at which this reduction occurs, and it is given by Nernst's equation. If we think of writing this equation for copper, then 0.34 is the standard potential for the reduction of the copper, and by keeping other constants at 25 degrees centigrade or room temperature, for example, this equation is resulted. If you plot this equation, we see that above this, on the energy scale, above this, corrosion occurs. Corrosion means ionization of the copper takes place, and below this, the reduction occurs or electroplating occurs. So what happens if we apply a potential between anode and cathode in which are dipped in the electrolyte? So initially the current rises linearly, steadily, and in this region you should be below this, of course, 0.35 volt. So in this region, the smooth and layered films are deposited and low deposition rates are there. And in the second region, oh, I'm sorry, somebody is doing something on the screen. Can somebody help me to remove that scratches? Hello? Hello?
Sorry, sir. I think one of the participant has done. I request all the participants, please don't use this
Pens.
yeah, pen there.
Yeah, sorry, sir.
Okay. So, I was talking of the polarization curves in the electrodeposition technique. So in the electrodeposition, we have the region between 0.3 and 4, where the mixed control over the mass transport is possible, and we need to put the potential below this line. So people always plot the cyclic voltagrams, and they observe the oxidation peak up on the upper side and reduction peak on the lower side. So we need to keep the potential of the reduction reaction. Theoretically also, it is possible to determine the potential for deposition from the Pobax or potential pH diagrams. So this is the Pobax diagram for the Fe water system, and this is the Pobax diagram for the CuOS system. So you can see the immunity, corrosion, or the passivation regions. So we need to choose passivation regions for the particular deposition. For example, if you want deposition of iron, then you can choose this region. For Fe2O3, you can choose this region. For example, in CuO system, you can have either copper oxide, different phases, the copper deposition. This is the corrosion region, and this is the passivation region of the copper sulfate. For copper indium diselenide, this is the common region, and I have juxtaposed the three Pobax diagram, and we can keep any potential between this for corresponding pH and have the simultaneous co-deposition of copper indium selenide. So with the help of this electrodeposition technique, generally the chalcogen earthen film, chalcogens are sulfur, selenium, and tellurium. most of the chalcogen thin film materials, they are deposited. And here I have given you for your reference the uh, review articles by Professor Lokhande and other review article which is recently published. Next is the chemical bath deposition, where we just immerse a substrate in the chemical or the ions containing the bath containing the ion. Sorry. So there are many advantages of the method. Only few I wish to tell. We can have the number of substrates simultaneously. We can have the simultaneous deposition on many substrates. We can avoid oxidation and corrosion because this deposition takes place at room temperature. And we can have pinhole and uniform deposit with the help of chemical bath deposition. This is also called as solution growth or simply chemical deposition. And metal chalcogenide thin films are extensively deposited with the help of this method. And for example, if you want to deposit cadmium sulfide, then you can take the cadmium acetate or cadmium chloride or other salt of cadmium, and the salt like thiourea, thiostamide, thiosulfate, and sodium sulfate or other as the sulfur source. In this deposition, the two products called as ionic products and the solubility products are of paramount importance. If both the products are same, then we call solution is saturated. If the solubility product is greater than ionic product, then it is undersaturated. And for in the chemical bath deposition, to have the deposition, we need this ratio or this product, ionic product should be greater than the solubility product. Here the experimental setup of chemical bath deposition method is shown, where there is a provision for measuring the temperature, keeping temperature constant, rotating or stirring the solution. This is the thin film or substrate. There is a provision for rotating the substrate as well. The way in which deposition continues in the chemical bath deposition is via different processes called as migration, aggregation, nucleation, growth, coalescence, and film formation. Now here I have given you for comparison the photograph of chemical bath deposited cadmium sulfide thin films and electrodeposited cadmium sulfide thin film. The surface on which you are going to deposit the material via chemical bath deposition technique should be hydrophilic. If it is hydrophobic, then no condensation will take place. But if it is hydrophilic, then the condensation takes place and we get the film deposition. With the help of this method, the metal sulfide, metal selenide, mixed metal chalcogenide thin films, even metal oxide thin films are deposited. And the review article by Mane and Lokhande is given in this slide. Here are some of our results of our lab. We have published these results also. So with the help of this chemical bath deposition method, we have prepared zinc oxide thin films. We know preparation of zinc oxide at room temperature is not possible. But what we can deposit at room temperature is the zinc hydroxide, and subsequently these hydroxide thin films are sintered at the optimized temperature, and very uniform and very adherent and highly crystalline films of zinc oxide, they are resulted. You see, doping is very simple in chemical bath deposited, and with the help of doping and properly optimizing the preparative parameters of the thin chemical bath deposition method, we can have a nice architecture, a nice morphology. This you can see cauliflower-like or the sponge-like morphology, and even zinc oxide nanorods, zinc oxide hexagons are observed for the films deposited with the help of chemical bath deposition. Next is the advanced or modified chemical bar deposition, also called as Silar method, where the cationic ionic precursor, they are not mixed before deposition. So they are separately kept. There is a reason for this. This Silar method is abbreviated as Silar because it is successive ionic layer adsorption and reaction method. Now we know in the chemical bar deposition, homogeneous or heterogeneous nucleation takes place. Homo means in the same medium, hetero means at the interface between two medium, solid and liquid, for example. So if it is heterogeneous nucleation, then king deposition takes place. But it is if it is homogeneous, then bulk precipitation takes place, and we have loss of material, and this is one of the disadvantages of this method. Therefore, to avoid such problem, Silar method was developed, and it is also called as modified version of the chemical bar deposition. Where in this, another advantage of this method is water insoluble ionic solids also can be deposited, and the materials deposited with the help of this method, they are metal, semiconductor, ceramic, superconductor, conducting polymers, etc. So when we form the junction between the electrolyte and metal, for example, then the two layers, Helmholtz layers, inner Helmholtz layer and outer Helmholtz layer, which contains solvated molecules of cations, and this. So this important layer formation is the crucial part of formation of a thin film in this Shila. So the rate of deposition can be controlled. The stoichiometry of the films can be controlled. This is the greatest advantage of the Shila method. So what are the steps involved in the Shila? Yeah, adsorption. The cationic ions are there adsorbed. The films are again rinsed in the double distilled water, where loosely bound cations, they are removed. Again, this substrate, they are dipped in the anionic precursor, where reaction with cations occurs, and again they are rinsed, and this is repeated until you get a very uniform thin film. You can have simultaneous deposition of many cations as well in this method. For example, in case of CZTS method, where the deposition of cations like copper, tin, zinc, and the anion sulfur is made in the sequence such that in the first dip, copper and tin is deposited, then rinsed, then reaction with sulfur, then rinsing, then adsorption of zinc, then rinsing, then reaction with S2 minus and rinsing, and in this way CZTS thin films also are deposited with the help of Silar technique. This is the instrument where you can have the atomization, the substrate, you can substrate holder can be rotated or it can be moved linearly over the beakers. The concentration of the ion is a very important influencing factor in the Silar method. If we increase the concentration of the ion, the thickness increases, but there are chances that we may lose this stoichiometry. Adsorption and reaction rates, they should be balanced for getting uniform films. Rinsing time is very important. If the temperature is increased, then the high rate of depositions are achieved, but we should optimize the temperature of the deposition. With the help of complexing agent, the rate of reaction can be controlled. Of course, sulfide, selenide, chalcogenide, composite, metal oxide thin films are deposited with the help of Silar. And here I have given the reference of the review article in which the information about the Silar is given. We have prepared the zinc oxide thin films with the help of Silar technique. And you can see in one of my earlier slides, I have shown the morphology of the zinc oxide thin films prepared with the help of CBD technique. And you can see the morphology of the zinc oxide thin film prepared with this modified CBD or Silar technique. So it has changed dramatically. We have used this zinc oxide thin film deposited with Silar in the metal semiconductor metal type of device for UV detection. Next is the thermal spray coating or spray paralysis technique. Here, the chemicals are taken and the chemicals are sprayed over the hot substrate. Paralytic decomposition occurs and very well adherent thin films are resulted. So as I said, the precursor solution is polarized by means of a neutral gas, for example, nitrogen, and the fine droplets of the precursor solution, they fall on the substrate, and the volatile byproduct, they are evolved from the exhaust. We can have vertical or slanted deposition method also. We have vertically downward and vertically upward deposition methods also. We can have stationary nozzle or we can have linearly moving spray nozzle. Various deposition parameters, they are listed here, and of these, the substrate temperature is very crucial. For every deposition, we need to optimize the substrate temperature. It is unique for a given material. What are advantages? Of course, this method is low cost method. Doping is easy. Uniform thickness can be achieved. Vacuum is not needed. Adherent films are resulted. We can have composition gradient across the film. We can have the layered films. And this method, it operates at moderate temperature. This temperature moderate, I mean, is relatively less than the chemical vapor deposition method. And this is the small animation which I have prepared for the spray paralysis. When a compressed air it rushes out from the outer part of the nozzle, then the vacuum is created at the tip of the nozzle, which pulls whole air column from the liquid, and the whole liquid is pulled, and the liquid fine droplets are spread over the hot substrate, and we get a very uniform and adherent thin film deposition. This is the block diagram. The important parameter in the spray paralysis technique is the droplet size. So here I have showed two approaches. One, at fixed droplet size, if you increase substrate temperature, and at fixed temperature, if we decrease the droplet size, what happens? So at fixed droplet size, if we increase the temperature, then the homogeneous reaction starts occurring. Means the reaction of the ingredient, it occurs in the hot atmosphere above the substrate, and only powder is spread, which results into powdery deposits. If the homogeneous reaction, heterogeneous reaction at the interface of substrate and air, if it occurs, then the very good, excellent film formation takes place. And this is the same is the case in this case, where we keep substrate temperature constant, and if we decrease the droplet size, then we need to optimize the substrate temperature and thereby the droplet size. And with the droplet size, typical droplet size is of the order of few micrometer. When the deposition occurs, the energy required for the decomposition and subsequent recrystallization is given by the hot substrate. So deposition, then crystallization, and then recrystallization, and the formation of larger growth. This is the sequence of the film formation in the spray paralysis. This main advantage of this spray paralysis technique is that we can have the deposition over very large substrates. And here I have given you the photograph of the film prepared in our laboratory on 10 centimeter by 10 centimeter substrate. And this is the greatest advantage. Another advantage of the spray paralysis method is that these methods, they are want to produce oxide thin films if the deposition occurs at ambient atmosphere, in an ambient atmosphere. So this is the photograph of the FTO glass, and this is the photograph of the zinc oxide deposited over FTO glass. As I said, vertically downward and vertically upward spray deposition. So this is the one of the advanced technique where the nozzle is kept below and deposition substrates are kept above. So it is against gravity. Here it was possible to control the droplet size and the deposition rate of the spray deposited thin films. most of the oxides, many oxides, of course, I have given you the list of the oxide deposited and listed in this review article by Professor Pramod S. Patil. And if we use the inert gas as the carrier gas, then it is possible to deposit chalcogenide thin films also. With the help of this spray paralysis technique, we have prepared high quality, having high figure of merit, FTO thin films. Various parameters are optimized, and we could achieve the sheet resistance of the order of 5 ohm per square in case of FTO. In case of ITO, tin doped indium oxide, we could achieve the resistance of the order of 4 ohm per square. In case of zinc oxide, the resistivity of the order of 10 to the power minus 2 per ohm per ohm centimeter was achieved. And you can see the films are highly crystalline, C-axis oriented thin films, and the deposition was, the growth was perpendicular to the substrate surface. And this is the photograph of the various films, which representative films which were prepared in our lab. The extreme right is the photograph of the ITO film, and extreme left is the photograph of the cadmium oxide thin film. So what you can see, the films which are highly transparent are less conductive. So, but with the help of monitoring the preparative parameters, it was possible for us to increase transparency as well as conductivity in case of transparent conducting oxides. So these films were used in the chemical gas sensors, particularly cadmium indium oxide, zinc oxide, doped zinc oxide, ferrite thin films, doped tin oxide, tungsten trioxide. These are the films which we have tried in our lab to use them in the chemical gas sensor. We have used the spray deposited thin films as the transparent conducting oxides or the photocatalysts which are transparent, mainly TiO2, iron oxide, zinc oxide, tungsten trioxide, doped these films and the composite between various films in the photocatalysis, where the prototype reactor for water purification was constructed in our lab. And this is the list of the publication based on the papers on photocatalysis, and the photocatalysts were prepared with the help of spray paralysis technique. And since last 10 years, you can see we are working continuously on TiO2, iron oxide, zinc oxide, tungsten trioxide. And recently, we have started working on ternary oxide like bismuth tungsten. We have used these films in photoconductive UV detector. Of course, we have used other films also. Here I have presented the results of the spray deposited zinc oxide. So zinc oxide prepared by spray paralysis was used in the UV photoconductive detector. The missing link between the fundamental electric elements R, C and L are the basic circuit element, electronic circuit elements we know. But the memristor also is the basic circuit element, where resistance depends on the history of the applied voltage and the current. So we have used the metal oxide based thin films prepared with the help of spray paralysis technique in memristor application. And this is the list of the publication, particularly ferrite on copper oxide, tungsten trioxide, zinc oxide, titanium oxide, hafnium oxide. These were tried as the memristor. And here I have showed the comparison of the work carried out by the spray paralysis technique in our laboratory. And you can see most of the work is on transparent conducting oxide, solar cell, photoelectrocatalysis, gas sensors, composites, UV detector, and memristor. Next is the sol gel method, where in the solution monomers are formed in the colloidal solution, that is sol. Sol gets converted into gel, and this jelly solution is very crucial in controlling the reaction, the size of the particles which are prepared with the help of this sol gel method. Here I have showed the schematic representation of the different stages and the routes of the sol gel technology. So a sol when it is aged, it forms the gel. If this gel is naturally dried, or when the solvent inside the gel, it evaporates, then dense ceramic is formed. If this solvent is taken supercritically, then aerogels are formed. If this jelly media is used for precipitation, controlled precipitation, then it is possible to make nanoparticles with the help of this method. But if this sol, where the hydrolysis and polycondensation reaction takes place, is used as the precursor for the film formation, where the substrates are dipped and dried, then zero gel films are formed. Further, after heat treatment, a dense ceramic thin films are resulted. Or you can put a drop of this sol on the spinning substrate, then the ceramic films are possible. So there are two approaches as far as the sol gel methods are concerned. One is dip coating, other is spin coating. In the sol gel method, it is also called as wet chemical method, where solids are suspended in a liquid solvent and neck growth takes place and it converts into gel. So colloidal solution turns into integrated network, and where the hydrolysis reaction takes place and polycondensation reaction. Hydrolysis means reaction of a water, and this bond is broken and this R is replaced by OH. When such molecules they combine in a huge number, it is called as polycondensation. So hydrolysis and polycondensation is the heart of the reactions or the main reactions in the sol gel method. So two approaches, dip and spin coating. The first approach is the dip. Of course, this is, in this method, low temperature is needed. Coating on vast surface is simple. We can have deposition of a very small thickness of the order of 10 nanometer with the help of this method, where the stages are dipping, deposition or drainage, and evaporation. These sol gel deposited thin films, they are further sintered to get dense films. These generally substrates are drawn vertically with the rate of 10 mm per second or so, and thickness can be fine-tuned. The angle of withdrawal also is very important. Here I have shown the photograph of the equipment which has been supplied by the Hallmark company, and is the corresponding schematic representation, where we have sol, then these are the substrates, the heating mechanism and the cooling mechanism and temperature controller mechanism. The important factors are pH, solvent, time, and temperature. In this, the important one is the pH. We know any colloidal chemistry that involves water sensitive is sensitive to the pH. And temperature also is very important. Time slower is better, of course. Main advantage is we can have multi-layer deposit with the help of dip coating technique. But it is not possible to have many deposits, say for example more than 15. So this is one of the disadvantages. These are the results of the deep coated TiO2 thin films prepared in our group, and these films, they are used in UV detector. You can see the morphology. Next is the spin coating technique. It's also called as the spin casting. What the main or the important aspect of this technique is, we remove a solvent by spinning the substrate at very high speed. The films are generally rotated at the speed of say 1000 rotations per minute, so at such a high speed. So deposition, we put a sol in the form of a drop on the substrate. The substrates are spinned, and the curing. These are the 4 stages. First one is we keep a solution on the substrate, then the acceleration of the substrates. It is also called as a spin up, where thinning of the liquid film takes place. Next is the solidification. It is also solidification region, and this saturation of the solidification and thin film formation takes place. So these are the 4 stages: solution on the substrate, acceleration, still spinning, and solvent evaporation. Deposition, spin up, spin off, and evaporation. So generally, the solvents which are easily evaporable, they are preferred in this method, particularly chloroform, methanol, acetone, and toluene are the typical solvents used in this deposition. Of course, the substrate to solution interface interactions are more stronger than solution to air interface. And with respect to time, we know the concentration of the solution decreases and the viscosity changes, and which changes the rheology of the solution. Generally, for example, here I have taken example of indium oxide reported in this paper, where they have one deposition, then preheating 200 degree, 250 degree centigrade for 10 minutes, again deposition, again. So this step is repeated for 6 times, for example, and further it is sintered to have a very uniform indium oxide thin. So this repetition also is suggested for having a larger thickness thin films. So one of the disadvantages of this technique is you cannot have the deposits of very high thickness. But the advantage is we can have the thickness, lower thickness thin films. Spinning speed, of course, as I said, the acceleration is very important. 50% of the solvent will be evaporated in the first few seconds. And this acceleration provides the twisting force. Fume exhaust is needed. We can have the deposition over mass, wafers, slides. Etching is possible with the help of spin coating. And as I said, the thickness less than 10 nanometer is it's possible with the help of spin technique. But this method is less material efficient. Only single substrate can be used. And due to fast drying, if you aim to prepare nanocrystalline thin films, microcrystalline films results. So you need to have a better control over the preparative parameters. And this is the last method which I am going to explain. It is called as hydrothermal method. Hydro means water, thermal means treatment. And homogeneous reaction occurs at relatively higher pressure and temperature inside the autoclave. And we take the solvent to the supercritical stage, and we have better control over the chemical reaction between precursors. This is the main idea of the hydrothermal method. The another beauty of this technique is we can have variety of the morphology, decorative morphology, you can say, or needed morphology in various devices can be achieved with the help of hydrothermal method. Here, heterogeneous reaction at the interface between solid and liquid is and the high pressure improves the arrangement of the molecules. Films are very much adhesive films, and we take the solvent to the supercritical stage, and therefore the material formation takes place in the supercritical. So this supercritical region is the region after triple point. If you see the phase diagram, there is one region called as supercritical region, beyond which we cannot distinguish between a liquid and a vapor phase. If you take solvent to that stage, then it is possible to tune the properties of the materials. And here various growth stages in case of the hydrothermal method, they are shown: surface diffusion, arrival of the atom, then surface diffusion, then nucleation, and then layer by layer deposition. This is the photograph of the hydrothermal instrument. We have nut bolt type of autoclave, or you can have thread type of autoclave also. pH, concentration, time, and temperature, very similar to earlier method. This here also, these are the crucial parameters. But disadvantage are when this is time consuming method, high pressure requirement, and impurities can reduce crystal quality. So these are few disadvantages of this method. We have prepared TiO2 thin films. You can see the morphology of the thin films of TiO2 prepared by hydrothermal. Earlier I have showed the morphology of TiO2 thin film prepared by other technique, other chemical, spin technique, for example. And here you can see. So we can have better control over, or you can tailor the morphology of the surface of the thin films by the various chemical methods. This is my group, research group, and these are the students who are currently working under my guidance. We know coronavirus pandemic has a lot of dark sides, but always we look on the bright side of the life, and this virtual conference is one way to ride over this pandemic. So once again, I thank all organizers and all the listeners for their patient listening. So I hand over the session to the organizers for further. If there are some questions, I will be very much happy to answer them.
Thank you so much, sir. If there is any question, please, you can type it in the chat box.
I think there are a few questions in chat box. I think there are no questions in two situations. Either information is completely understood or it is not understood at all.
No, sir. It is indeed a very, very clear explanation. You did it in a very diligent way. You conveyed it because it's virtual. You were very moderate in your talk, and you showed the methods, clear pictures, everything. So it absolutely made very clear.
Thank you very much, madam.
Thank you so much, sir. Thank you so much. If there is any questions, you can please type it in the chat box. We can take it later also. Thank you so much, sir. Now we will break for lunch, and we will meet again at 2 o'clock. I request all the participants to log in 15 minutes before so that to have a session from the beginning itself. Thank you so much.
Thank you.
Same link only you can log in. Okay, same link, you please log in. Around 2 o'clock, we will start our session again, same link. 15 minutes before, you please log in, all of you. Thank you so much. The feedbacks will be sent in the afternoon session only, feedback link. It will be put here, it will be given here in the chat box in the afternoon session. So please log in. Thank you.
Hi, can you hear me? Can you hear me? Okay. Um,
Welcome back after the lunch break. It gives me immense pleasure in welcoming our next speaker for the day, Professor Mark Sikorski. A very good morning to you, sir, in Poland. Now, our professor Marek Sikorski has its master's from Faculty of Physics, Poland, and he has a master's, and sir has done his doctoral degree in chemistry, and sir also holds a doctoral degree in science, and Professor has won many awards, a Royal Society and Foreign and Commonwealth Office Postdoctoral Fellowship, and Journal Grant for International Authors, Royal Society of Chemistry, and Fulbright Fellowship, University of Notre in USA. And sir has expertise in reviewing many journals, and his research interests include spectroscopy, singlet oxygen, flavin spectroscopy, fluorescence, transient absorption, photochemistry, and so on and so forth. Sir has guided many projects. He has published more papers, more than 120 papers, many review articles he has reviewed, and sir has edited many books. So it's very grateful and happy to have you here, sir. Thank you so much for accepting our invitation and joining in our international conference. I thank you so much, sir, and I will ask you to deliver your lecture on tuning spectroscopy and photochemistry of flavins. Over to you, sir. Thank you so much.
So thank you very much. It is my great pleasure to be here, especially at this wonderful conference, Advanced Material Science and Application. And thank you to all organizers, and especially the chairman, Mr. Jayarama, and Sir Sitharam, Vice Chairman, and all organizers who allow me to present the lecture on this conference here. What I would like to talk today, just a second. It's like you said, lady, that is that tuning spectroscopy and photochemistry of flavins. And that is a sort of a history staying after this subject here, especially here in Poznań in Poland, which we do for many years of the research for that type of compounds. Isoentalloxazines are closely related compounds representing two classes of nitrogen heterocycles with active centers at the N1 and 10 and 3 and 5 and at both carbonyl oxygen at position of 2 and 4. Isoalloxazines are, and especially flavins, possess the yellow chromophores characteristic of flavoproteins, which are enzymes occurring widely in animals and plants. The early interest in photochemistry and photophysics of alloxazines, including lumicrom, mostly come as its relation to the flavins and mostly as their photoproducts. It has been important to assess that the toxicity of lumicrom and most of the alloxazines and also flavins they are not toxic, they are non-mutagenotoxic and non-clusterogenic. Alloxazines can be associated to flavins in many organisms and may be involved in some biological processes. Flavins and 5-DASA flavins are components of blue light sensing receptor belonging to the low domain and blue domain. They are involved in many important biological phenomena such as phototropism, chloroplast movements, and adjustment of organism in critical cycle. That is giving us a sort of impact to think about flavins on a little bit new way. Despite increasing attention, the research on application of flavin in organic photocatalysis faces several changes. And those are the photochemical stability, the solubility, redox properties, molecular structure. And the aim of our research is to formulate some sort of principles or guidelines for building such molecules which will be much more cheaper to synthesize much more stable in application, much more soluble in common solvents, and will have the properties of which we desire. So usually it means that they should absorb the light in a visible range, allowing us to use low cost of light sources and low cost of the glass instrument and all the other stuff connected to the excitation of a molecules such a kind. So that presentation will be somehow guided you through the flavin structure, and I will give a little bit of impact on how to apply them in a more common sense in a few type of research which we conducted. Sometimes we are just in time of doing those type of research. Here you can see a little bit of flavins, which of course are connected to FMN and fat. And flavins are also belong among the most prominent natural chromophores. So that is the sum of the core impact on our interest to that. They occur naturally in many systems, so they are not as so harmful to the system which we can implement them in the future. And all of those compounds from a broad family of flavins derivatives which are together with some flavin salts, which are also presented on this slide, which we have found recently as some of the most prominent compounds to many of the application. I will try to guide you later on this lecture. One of the recent, up to the recent time, it was the only riboflavin tetraacetate and its derivative, free methyl, the riboflavin tetraacetylate, which were used in photocatalysis. The reason why is simply to understand that that was mainly only two flavin compounds from a flavin family compounds, which were pretty stable. That you can see on this picture, on this slide, which we compare the photostability of tetraacetyl riboflavin with riboflavin itself. Riboflavin and most of the flavins are easy to degrade, are easy to decompose. So they, the utility of them or use of them is a little bit limited by its photochemical stability. So recently we have found that this flavinium salts, which I have presented you, are some of the also prominent for the future used in photocatalysis. We do this, a lot of this laboratory work, synthesis work, in a close collaboration with the people from Prague, from a group of Professor Radek Cibulka, when we have a strong collaboration of doing this all things together, starting from the synthesis up to the application, up to the characterization of the properties of the compounds here on that. One of the application which is really on the topic now for a flavin type of compounds is just using them to in a organic photocatalysis, and especially to one of the examples here which I am presenting is just to photooxidize the sulfide to sulfur oxides. So that is the conversion of the relatively strongly reacting compounds to something what is less harmful to the environment. We usually started from a combination of checking some impact of checking the system which will allow us the most efficient way to convert such sulfides. And finally, we have found that this is one of the best system to use is just the mixture of acetonitrile and water in the properties 85 to 15. So which will allow us to photooxidide sulfides in a very efficient way. Just to test, like usually we should do, or we at least do by ourselves, we did some checking experiment when we just check if these three factors are necessary altogether to make the reaction to occur. And as you can see, it's done and it's shown by this slide that only when the catalysis is present, oxygen is present, and the light is present, we can convert the thioanisole in such a case almost in a conversion up to the 100. So the fully successful on a very low short life time of irradiation, something like 30 minutes, and using just a conventional bubble and conventional light source like LED, so it is not necessary to use any much of more expensive light sources in such an experiment too. So on that slide, we are presenting some of the result and the yield of the conversion of the substrate in all of the cases. And the catalysis, like I told, is just riboflavin tetraacetate in such a case, one of those of the most stable compounds from the class of flavin. Recently, we did several another papers and several another studies showing that the flavinium salts are even sometimes better catalysts than this tetraacetyl riboflavin itself. How to compare this to the results of some other scientists which were trying to do the similar task? You can see that in our case, the conversion of the substrate is taking only up to something like 15 minutes in comparison to the previous report on the same for the same system, up to something like 12 hours, 24 hours, 6 hours, 10 hours, just to what from those presented on this table. So our system has been very effective on somehow. We were also trying to get a little bit of insight of a mechanism of how it is going, what is the mechanism of the conversion. And we did some photochemical and photophysical measurements on such a way. We did some measurements of a singlet oxygen and many others. And we come to the conclusion, at least, that this is, at least for that system, the system is going on the reaction, which I schematically draw on this slide on the top of that slide, but telling briefly is that the electron transfer and the singlet oxygen pathway are both involved in the photochemistry of the system. So from a point of photochemistry, we will say that the photooxidation on the path 1, electron transfer, or with the singlet oxygen, both are involved in that system. Flavin-based organocatalysis and photocatalysis have been investigated intensively with the last 15 years. On that slide here, I am just giving a little bit of feeling you how much of different compounds we have already synthesized and we have tested in our laboratories from a point of the photocatalysis and many other applications. Some important results include, for example, developmental of sulfooxidation methodologies or finding excited flavinium salt like the 6 and 7 as extremely strong oxidizing agents. In intensive studies, we have determined many spectral and photochemical properties of flavin type of compounds. And in our past studies, we were interested in the effect of nature and position of substituent of on a spectroscopy and photochemistry of flavins. And in general, our general aim was to characterize and reconcile the diversity of photochemistry and spectroscopy of flavins in solution, with special attention to the singlet oxygen, with the singlet oxygen to determine the electronic transitions. And we conduct quite a lot of calculation for flavins, so it is some sort of quantum mechanical studies which are also involved in all of that what we are presenting. And also we are interested in from a point of photocatalysis on the photochemistry and also on a singlet oxygen production by such compounds like here. One of the relatively well known example of also the catalytic process in which alloxazins are involved is proton transfer and especially the reaction in the excited state. So something what we call excited state double proton transfer. When we moved the proton from a position of N1 to the position of N10. To do that, we need to have some compounds which will allow to build such a structure, such a bridge between these two positions. And in that case, it has been found that carboxylic acid are very useful. And especially acetic acid is something what we used most frequently, or formic acid as well. And that is the reaction which we also are very proud to discover here in Poznan, because we believe it is one of the almost the first system after the Kasha achievements for the to show the first his papers on excited state double proton transfer. The alloxazins are probably the second system in which this reaction has been discovered. How it is going on. Alloxazins are having emission at the shorter wavelengths, like on the slide is presented on a blue one color. If you add acetic acid, you will see that this emission on the blue side is going to be diminished and some new bounds is going to appear. And this new bounds is characteristic for isoalloxazins, for flavins really. So that is something what we can observe in the case of alloxazins. Just to remind some of you from a point of interest that it could be some sort of non-catalytic type proton transfer in the case of alloxazins when they form such a dimers like presented here on this slide. And in such a way, you can convert two molecules of alloxazinic type to the two molecules of something like isoalloxazenic type. But because of both molecules are going to be changed and they change the structure, and so that we call non-catalytic type. Because, and just to say, why we study that? Why we are interested in that? Proton transfer, for example, in excited. Oh, that is because that could remind or replace or mimic a very well system in biology. Especially the alloxazine or lumicron can be used as mimicking the properties of thymine, which is just presented on this slide. And that is indeed, we can put the lumicron or alloxazine to the DNA strange, and we can observe some formation of complexes of such a structure. And the binding constant for lumicron in such a complexes is pretty high, and so it's showing that this is reality to use some sort of alloxazines or lumicron. In that case, lumicron appears to be much better working for replacing the thymine in some DNA studies. Let's back to the proton transfer. I told that in the case of, in the presence of acetic acid, the longer wavelengths is going to appear and is going to up. So it is something like I presented on this slide here in solution, or something what I presented here in the crystals. To telling that it is not a speculation, of course, we did some measurement of a crystal structure for lumicron, and we have been happy to register the presence of some crystals on some sort of complexes of dimers, which are pretty allowing such a proton transfer in such dimers in solids. But that is another story, which maybe is interesting, but I will not talk on this lecture today. Let's go to the solution with acetic acid. So it, of course, did it in a time-resolved manner, so we also measured the lifetime on a shorter wavelengths, on a longer wavelengths, just to check the kinetics of alloxazenic site on the isoalloxazenic emission, and that all is just giving us, especially the most meaningful are the measurements at this longer wavelengths, when we see the rise and decay, like here, we see the rise and decay. So that is indicating us some sort of connection between these two molecules in excited state, between this alloxazenic form in excited state and this isoalloxazenic type of molecule in excited state. So that what we are talking is really the excited state reaction which take place in the presence of acetic acid as a catalyst in such a case. I thought that we are also focused on molecular structures, on providing the good molecules to study the system we are interested. So here I am presenting the 4 molecules which have been chosen for a special reason to be implemented in such a studies of proton transfer in excited state. So let's see, that is a lumicron, 3-methyl lumicron with a methyl group here, 1-methyl lumicron, which have a methyl group in that position, and 1 3-dimethyl lumicron, which have a methyl group in position of 1 and 3. So those 2 molecules are obviously molecules which prevent the proton transfer in excited states. That molecules are not allowing any proton transfer from N1 to N10 because of structure modification. The same is with that molecule. In this 2 on the top, the proton transfer, if it is going via the N1 and N10 molecules, which for some could be the question, because it could be many positions involved in such a molecules for such a reaction. So let's see. So those are the time-resolved spectra taken after 1 nanosecond, after 1 nanosecond, after 1 nanosecond for a lumicron free methyl, and so without acetic acid. And that is the most important part, because we add acetic acid, and what we see, the top 2 molecules, we see this new bounce which is going to appear, new bounce is going to appear, and here no changes, no changes. So that is some sort of extra proof that what we are talking about, the proton transfer in excited state, is a reality, and it is connected to the position N1 and N10, if someone would have the question on that. Something more, we can still make a little bit of modification of the molecules just to remove nitrogen from a position of N5 to see if that, which also takes some modification and effect on the reaction which we are interested. And just see on this 3 molecules, once again chosen for a special reason. That molecules allow the proton transfer from an N1 to N10 position, that is preventing that reaction, and that one is mimicking somehow the isoalloxazenic type of structure. So that molecule is a little bit of like the molecule after the proton transfer has occurred. And looks how the data looks. When we add, that is the isoalloxazenic type compounds, the absorption, here is the emission from that compound, and here is the emission of 5-diaza when we add acetic acid to that. So that bounce is going down, that is going up, and look on that spectrum of emission. Here on a 1,3-dimethyl substituted diazoxazine, when we prevent the proton transfer. So we add acetic acid and no changes on the emission at all. Here are some of the reactions to tell us that this reaction is going in a complexes like 1-to-1. Here are some of the reactions to showing us that this is the reality. So we measured the lifetime of, we got the double exponential kinetics on a longer wavelengths here on that bounce. So we get some sort of extraordinary proof of the proton transfer in excited state. And now I will move to something a little bit different, because now I will say, okay, we did quite a lot of work from experimental point of view. Now I would say, let's see what we did on from a point of theoretical calculation. And we were checking almost all the complexes which are possible to form between 5-diaza derivatives and formic acid. And what we did one complex, another. So it is something like 6 complexes which in theory can be formed. But our results indicate also from the experiment, but also from a theory, that only the complexes on a position of 1 and 10 between the diazoxazine and acetic acid or formic acid is stable and is favorable in taking place, because it is some sort of the energies of the complexes of a normal form and the form after the tautomerization took place. Once again, the normal form, tautomerization, but the complex between in the position of 1 and 2, 3 and 2, 3 and 2, 3 and 4, 4, and so and so. And from that, we are arriving to the distribution curve, which are showing us a reaction pathway of a proton transfer from a position of 1 to position of 10. And this is those picture is presenting the reaction pathway in a ground state and is showing us what we expect. that the molecule of such a kind is lower in energy than the molecule of such a kind. Why? Because I didn't tell till to now, the proton transfer in excited states finished in that molecule again. So that is the precursor of the reaction, and that is a substrate of reaction as well, the final. So we don't have any photochemistry involved in that way. That is the pathway for the excited state. Here is a difference because that molecules, the molecules of a normal structure is having higher energy than that of isoalloxazonic type after tautomerization. Here are the numbers, here are the details of the calculation. All the calculations have been done in Turbomol 66 software patch, and we did it in something like triple zeta condition, and so those are pretty good results to show to support our hypothesis about the proton transfer in excited state. So finally, we come to a very simple model, just like that one. 4 molecules, that one in the ground state, excited state of the alloxazonic form, a movement to the isoalloxazonic type of molecule, movement, the relaxation to the ground state, but this ground state is also relaxing to the alloxazonic molecule which we started all this from. So that is just about the proton transfer in excited state for the alloxazines. To tell a little bit more on that, we did a lot of work on a calculation, on a theoretical point, and also on the experimental part, just to record the spectra and the photophysical properties. But what is the most important? Most important is that some of the data are easy to interpret from a point of experiment and a theory. Especially look on those few data which I'm presenting here, and look on the numbers which are connected to the, for example, lifetime. And you will see that the compounds number 1 and 4 are having the shortest lifetime. Here, 35 and 400 picoseconds. And those are 1 and 4 compounds. Why? Because the lowest singlet excited state, the first excited singlet state, is having the n-pi configuration. Look on those two. 2 and 4 and 8.9 nanoseconds, the longest lifetime recorded in experiment. What is going in the experiment? They are having the lowest state well separated from n-pi, and that is in character of pi star of having the character. Here are isoalloxazines compounds, which we also did for several things on. I probably have to just mention alloxazines and isoalloxazines are very much of different. But once again, on this slide, look on these 2 compounds. We choose especially the 2, which is 1,3-methyl-dimethyllumichrome, that one, and lumiflavin, 3-methyl-lumiflavin. What is the difference? The difference is only the position of this methyl group. In alloxazonic type of structure, it is in position of 1. In the isoalloxazonic type of structure is in position of 10. And that influences quantum fluorescence, lifetime, radiative, non-radiative, the wavelengths of emission and absorption as well. So we can modulate, we can tune the properties of compounds to the level or to the stage which we want. Tune and to show how we can tune the molecules of such a kind of structures like flavins, it is that kind of slide which I'm presenting now. And you see that we, on conventional way on the absorption spectra that we can tune the properties from something like 350 nanometers at a maximum to something like 450 on a maximum wave length of the absorption, which means we move toward to the red. What it means, we are able to use conventional conventional light sources like lamp, like diodes, whatever what is cheap. What is cheap and what is able to excite the molecules on a range of between high 400 or even longer, or invisible range, which is not always the case of the flavins. Another, what we can see from that slide, is that we can tune the energy of a triplet state here on that slide here, and that we can tune it from a lowest to somehow very high level. So by that, we can probably, you can just guess, we can probably just tune the properties of singlet oxygen production and as well. So on that way, we are just moving to the singlet oxygen now, which we are interested. Why? Because that will mean that whenever we use the flavins, we can use them as a sensitizer of a singlet oxygen. And if it is a case, it means we can use the reactivity of singlet oxygen to purify the water, to clean some system, to kill some mutagenic changes, to kill something whatever it is around the molecule of a sensitizer. So we used the flavins as a sensitizer for singlet oxygen production. To study the singlet oxygen production, we used the measurements of a lifetime of a singlet oxygen, or quantum yields, or the quantum yields of singlet oxygen measured by the spectra. That is relatively important to remember that to record singlet oxygen, you need to have a detector which allow you to measure the emission in a range of something like 100, 200, 1279 nanometers. So in near infrared. Remember, most of the detectors which you are using in conventional spectrophlorimeters are not allowing you to do that. That is also the question how expensive and how much you would like to spend money for such a kind of detectors, but that is another story, which I probably will not go to the details. We used some Hamamatsu detectors, which I believe are at this moment one of the best for the detection of a singlet oxygen. And we do the measurements in comparison to the standard, to the perinaphtenon, which is a very well accepted standard for a singlet oxygen measurements as well. And we used some method of a gradient, which is allowing us to do that measurements on a relatively high precision. Something to remember, and something what was a little bit of surprising for us during the measurements, because the singlet oxygen lifetime is a characteristic property for a solvent in which you do the measurements. So it is not what is allowing you to characterize the sensitizer, photosensitizer, but the solvent. And that is something what is usually well known, that in acetonitrile, the lifetime of singlet oxygen is something like around 80-70 microseconds. But what we have discovered that the effect of a lifetime of singlet oxygen in acetonitrile depend on the remaining water which is in the solvent. And even if it is relatively, on normal circumstances, you probably will use the solvent which has something like 1.2 or 2.5 of water in acetonitrile. But in such a case, you will record the lifetime of a range of 65 or 72 or whatever microseconds. But if you will remove the water, even better, you will go to higher lifetime on that. And here is the results showing that this is really the reaction with the water, which is going in excited state. Do the measurement of singlet oxygen usually required also to make the measurement of a flash photolysis of recording the triplet properties? That is required because otherwise you will not be able to say if the limit which you have got is a limit of quantum units of intersystem crossing, the production of a triplet, or if it is a limit of a lifetime of your sensitizer in a triplet state. Because if it will be too short, you will get less singlet oxygen. If it will be longer, you probably will get more singlet oxygen on that way. So here is a sort of a slide which is telling sort of a strategy which we have found, just tuning the properties of flavins as regards of singlet oxygen quantum units. And in general, flavins, isoaloxazins are having a little bit lower quantum units in comparison to aloxazins, which sometimes have a very high, like 0.85, 0.93 quantum units of singlet oxygen production, which means it is really high. Just remember, perinaphtenon, the standard, is having the quantum units of singlet oxygen, which we usually commonly accept, of a value of 0.95. So that aloxazins in many cases are almost comparable to the standard molecule which you used. So what we are interested much in that, we are interested in tuning the properties of flavins from something what will give us the 100% of singlet oxygen production to almost non-production of singlet oxygen, to making them sensitive, like a probe for a fluorescence measurement, or just non-fluorescence at all, but just to produce some reactive oxygen species in the system we are interested. And something almost to go to the end, I would say, that is also some of the topic which recently we also are doing. We are just using the flavin in some red blood cells studies that would be deliberate a little bit more on just a methodology by my PhD student Amirali Davenport, and it will be done tomorrow on an oral presentation, I believe. So just be aware of that. Something more, some proteolytic equilibria, which also is important to remember for flavins, and especially, once again, choosing the proper molecules like lumichrome, 1-methyl lumichrome, 3-methyl lumichrome, allow you to see the anions of a specific properties of anions depending on the pH now. So you can just tune the pH and can have the molecule of properties of what you would like to have. And here are some of the results on that. Those results have been especially motivated by some of the papers which have been appeared, and mistakenly some authors have reported some numbers of pK value for neutral anionic equilibrium of lumichromes in a range of values something like 12. And so that is not the case. That is a case of d-anion. For anions, the pKa value is in a range of 8, which we are presenting here on this slide. And why is so important to choose the molecules properly? Because you can see, like here, the dependence of a pH, once again. Here you see almost the complex situation when the neutral form is present, anion on some stage, one anion, another anion, d-anions. But here, on the D part of the spectrum, you see 1,3-dimethyl lumichrome, which doesn't have any anion or the anion. It is only in a neutral form. So it doesn't fluctuate according to the pH changes on that. Some results of lifetime measurements on that. Some DASA, Lumicron in a short brief on that. And just to tell at the end, we do some other class of studies when we used our knowledge about the flavins. And we do that for a food analysis, for some edible oils, food products as more in general. That basically is telling we are coming to the end of my presentation, which is a little bit different from the previous one, because here I was just telling you how the playing with the molecules, how the playing with the knowledge of the basic of research can give you the advantage in some sort of application, in some sort of more specialized type of research. One of my PhD students will also present a poster on a proton transfer in excited state. Another one will present the poster on application of a modern technique for a food analysis. So also please pay attention to those two. I would like to thank Ewa Sikorska from Poznań, Radek Cybulka from Prague, Lucyna Mrówczyńska, Jacek Kolanowski, Gotthard Burdziński, Tomasz Pędziński, Rafał Bachosz, Dorota Prukała, Małgorzata Jasińska, Anna Golczak, most of them from Poland, and some foreign collaborators which also are involved in such a hand. It is Radek Cybulka, Ahmad Iqbal, Igor Chmieliński, Antonella Pascalona, De Caucalaire, Bordelande, Luis Filipe Ferreira from Portugal. Thank you very much for your attention.
Thank you so much, sir, for your informative and innovative research work. We are very happy and indeed privileged to listen to you, sir. Now, if there is any questions, the participant can put it in the chat box. If there is no question, then we will go on further thanking Professor Marek Sikorski for his wonderful presentation. Thank you so much, sir.
Thank you.
For accepting our invitation and presenting. Thank you so much.
It was always a pleasure to be on this conference, and it was only a pleasure to listen to such a prominent scientist on the row. Thank you very much.
That's very nice of you, sir. Thank you so much. Now we will have our oral presentation. The title of the paper for the first oral presentation is One-Step Preparation of Aqueous-Based Graphite Paste for Lower Cost Thermoelectrics from Dr. Rafiq Mullah, Swansea University, United Kingdom. Over to you, sir. Dr. Rafiq, sir.
Yes, ma'am. Thank you. Can I share my presentation?
Yeah, sir. Sir, you
yes,
can.
sir.
Thank you.
Rafiq Mullah.
Yes, sir.
Time is 8 minutes, Amma.
Yes, sir. Yes, 8 minutes.
Okay, 8 minutes, sir. Okay, Rafiq.
Okay.
And 2
yes, sir.
minutes for discussion. Okay.
So yeah.
We have a lot of introduction now.
Sir, your voice. Rafiq, sir, it is of 8 minutes presentation, and thereafter question answer session will be there.
Okay. Actually, I thought it is 15 minutes, so according to that, I prepared that. I will try to skip some of my time.
Okay.
Yeah,
Okay, try to
yeah.
be within 10 minutes, otherwise maximum 2-3 minutes we can give. Yeah. Thank you, sir.
Yes,
You can start.
Thank
sir.
you. Thank you. I just want to make sure that whether my slide is full screen.
Yes, sir. It is full screen. Yeah, you can start.
Thank you. Firstly, I would like to thank the organizers of this conference for giving me this opportunity. And yeah, here I'm presenting my work. It is about the preparation of aqueous-based graphite paste for lower cost thermoelectric materials. So before going into actual work, I will try to briefly explain about thermoelectric materials or thermoelectric devices. So in this thermoelectric, there are two words like heat and electricity. It is combination of heat and electricity. And the thermoelectric materials are the materials which can convert heat into electricity. Or more specifically, they actually need thermal gradients into electricity. So how they work? They work on the principle of thermoelectric effect. And this was discovered by Thomas Seebeck, a German physicist. So he observed that when a temperature gradient applied on the conductors, there is a diffusion of charge carriers from hot side to cold side, thereby generating some electric potential from the conductors. So this generated voltage is directly proportional to the gradient applied to the conductor. So when you apply more temperature gradient, you are going to get more voltage from the conductors. And when you take the ratio between the voltage generated to the temperature gradient applied to the conductor, this ratio is known as Seebeck coefficient. And this is given by delta V by delta T, means voltage divided by the temperature gradient applied. So basically, materials which produce more voltage from a small temperature gradient are better suitable for the applications. So people are looking for materials which can produce more voltage under small temperature gradients. So using that effect, one can make generators to convert heat into electric power. So that is quite interesting application of these thermoelectric materials. So this is a thermoelectric conductor. It's just like a battery. So in a normal battery, we have positive side, negative side. When you measure with a multimeter or voltmeter, you get the voltage of that battery. So similarly, when you put a conductor under temperature gradient, you are going to make a diffusion of charge carriers inside the conductor. And if it is n-type material, then negative charge carriers are going to diffuse from hot side to cold side. Thereby, a net negative charge will be created on the cold side. And deficiency of the negative charges creates a net positive charge on the hot side. And then you are going to get some voltage. It will be very less, few millivolts. That is not actually useful, sufficient enough to use for any applications. That's why we have to use more and more materials like this. So it's just like adding one more battery to get more voltage. So this is the one of the standard connection which is used in the thermoelectric generators. People use one side N-type, another side P-type. So in the N-type, negative charge carriers are going to diffuse from the hot side to cold side. And in the P-type, holes are going to diffuse from hot side to cold side. Thereby, we'll be getting negative, positive, negative, positive. It is a kind of series connection, just like here, negative, positive, again, negative, positive. So we can't use both sides N-type materials because the voltage generated by this will be cancelled by voltage generated by this. Ultimately, you are not going to get any voltage here. So in order to get more voltage, we have to use N-type, P-type, so that voltage of this and voltage of this will be added up and we get better output voltage. So to make it more clear, I used this concept. So if this thermoelectric material producing 5 millivolts under particular temperature gradient, and if this is producing about 5 millivolts, we are going to get about 10 millivolts total voltage. So if we want more and more voltage, this kind of connections we need to add in a large number, like hundreds of junctions. So this is a kind of one PN junction. So there are many PN junctions connected in series to get more voltage. So this is how thermoelectric generators are made. So these materials have very advantages because they they do not require any maintenance because it is just solid state construction and there is virtually no maintenance free. They are highly reliable because of the solid constructions and they do not release any gas, so environmental friendly, and they can work in aerospace, they can work in any orientation or zero gravity, and they do not need any solar light to work. So just heat somehow if we get, that is sufficient to use thermoelectric generators to produce electric potential or voltage for the applications. And they can also be useful for the places where there are no conventional energy sources are available. And most importantly, we are looking for this kind of applications where in our energy sector. So whatever energy is produced for our needs, most of it is getting lost in the form of waste heat, and that waste heat can be used by thermoelectric generators to convert that into useful electric power. Presently, there is one major issue that the thermoelectric technology is facing, that is the materials. The standard materials what we are using, what people are using in the commercial thermoelectric generators are based on bismuth telluride and lead telluride. And this kind of materials have many problems, such as toxicity of the heavy elements like lead and tellurium. The scarcity, tellurium is highly scarce, and there is a difficulty in processing and expensive raw materials or raw elements. Particularly, tellurium is an important element for thermoelectric devices, which is very, very expensive and as well as very scarce. So, for example, tellurium is its abundance is only 0.001 parts per million on the Earth crust, so which is even less than gold. So that is very concerning issue in the thermoelectric technology. So in order to avoid tellurium-based or any toxic materials, we are trying to work on low cost and abundant thermoelectric materials. Here in this work, we have started our work on carbon-based materials. So what we have done here is we just use graphite powder with a small amount of polymer stabilizer, then some amount of water, and we did a long duration ball milling, so about 1 to 2 days. So from that ball milling, finally we are getting a very aqueous based nice dispersion of graphite particles in water, and that can be coated on different substrate. We are presently using paper substrate, so we have got very nice coatings of graphite powder or graphite paint on the paper. So this is electrically conducting coating of graphite on the paper. They are quite flexible, and this kind of the graphite coated paper can be used for thermoelectric applications. So what we are working with that kind of graphite coated papers is given in this slide. So we are basically trying to make a PN junction like what I explained in previous slides. So our graphite film is basically P-type in nature, but another side we need N-type material. So both side graphite will not work. They cancel each other. The voltage will be canceled each other from the both legs. So that's why we need N-type. So in order to have N-type sample, the graphite film was treated with a polymer called polyethylene amine. So that polyethylene amine has a nitrogen-rich groups. Those are amine groups which are attached on the graphite, and they convert the P-type conductivity of the graphite into N-type conductivity of the graphite. More details are given in this paper. So by having this kind of connection, this is P-type, this is the N-type, and then we connect voltmeter, then we apply temperature gradient across the device, and by applying temperature gradient across the device, different temperatures across the device, we are going to measure the voltage generated from the device. So this is the graph which shows the linear increase in the voltage generation from the device. So you can see by increasing the temperature gradient, we are observing increase in the voltage generation. And there is also a small decrease in the resistance of the device. So internal resistance of the device has been measured with respect to temperature gradient. So this is required to calculate the power output of the device. Or in some cases, we can use short circuit current if the device is producing sufficient current. So by using this data, we have estimated the power output of the device, and about 50-degree Celsius difference, we are going to get, we are getting about 0.6 nanowatts of power. So this is quite low power, but this is for one junction, and that too graphite kind of materials, which is quite cheap and quite abundant and non-toxic material. And we are trying to, when we connect more and more thermoelectric legs, we can get more power output from the device. So we are also trying to add some impurities into graphite films while ball milling, so that we are expecting to get better power output from the device. So this work is still under progress. Due to COVID situation, we couldn't able to complete the work. The material characterization and the detailed analysis of the graphite paste is currently under progress. And despite their low power output, graphite or carbon-based materials can be very beneficial as they are non-toxic and abundant. But tuning their properties is very important in order to use them for the thermodynamic applications. And as a side, we are trying to incorporate different inorganic compounds, mainly metal oxides and metal sulfides, while milling, during the milling, so that we get uniform mixing of the inorganic compound with graphite paste, and we are expecting better performance from the devices from such materials. So these are some of the recent works. Yeah. Oh, finally, I would like to thank the European Regional Development Fund for funding our research project, and I would like to thank Swansea University for giving me opportunity to work as a postdoctoral fellow at the campus.
Thank you, sir.
I thank you all.
Thank you, sir. Now session is open for the question answer. So we have here our reviewer, Professor Nagbhushan, Department of Chemistry, RAMAIAH Institute of Technology, and Professor Siddharaju sir, Department of Mechanical Energy, RAMAIAH Institute of Technology. So I request both the reviewers they can ask the question to the oral speaker.
Okay. Rafiq,
yes, sir.
Your work is good, excellent.
Thank you, sir.
The
Thank you
topic
very much.
is very much suitable for present scenario because, as you all know, that storage batteries requires a lot of research is required. In that sense, what you have used is it is good work actually. As you said, lead, bismuth, all these things are replaced by something, and also tellurium is also very costly, as you said. But here I'm thinking about the applicability of the material, because you have chosen cellulose material, paper, correct? Na?
Yeah.
What about its stability? Is it withstand for a longer period? Can you use it for a longer period? Why can't you use some other substrate?
Yes, sir. So we can use, but basically what we are looking is the property of the material, not the final application. We are studying the property of the graphite paste at present. We have studied smooth surface. On smooth surface, the coating is not good at right now. But if we use screen printing or other techniques, we may get a nice coating of the films. But we are just using brush painting or just drop casting. For that purpose, we have used papers. But the fact is, these devices, once you make, they are quite like you are not going to disturb physically to those devices. You are going to only apply temperature gradient. You are not going to physically use repeatedly opening and all. There will be not such kind of usage. So paper-based devices also can be useful in these applications. But as you said, it is true that we should avoid such fragile substrate in order to get better life from the devices.
Any possibility of using other substrate? Possibility is there, na?
Yes, we can use the textiles instead of papers.
Correct.
Yeah.
Yes, correct. Yes. That is easily you can quote.
We are working. We are trying to use
even cotton. Even cotton will do. Correct, na?
Yes, sir. Yes.
Cotton will do. Yeah, definitely.
Yes, sir. Yes.
Yeah. Another thing is you have prepared a paste with PMMA. Correct, na? PMMA is water soluble, la? Polymethyl methacrylate.
Not PMMA, sir. That is PEI, polyethylenamide. That is for doping graphite from P type to N type. Yeah.
Okay.
Yes, sir.
Another question is you have studied temperature versus voltage performance, correct, na?
Yes, sir.
Yeah. According to your graph, as temperature increases, voltage performance is also increases. You show that around 50 degrees centigrade is around 2.5 volt, correct?
Yes, sir. Yes, sir. Millivolts.
What?
Millivolts.
Yeah. What about 50 degree means practically it is not usable, correct? Now, what about at room temperature? It is around 1.5 volt, correct? Na?
So,
Room temperature 35 degree.
Yeah, yeah. But yeah, we have to these devices are attached to the substrate where we are having waste heat generation, like any something like yeah. We can't use at just keeping at room temperature, it will not work. We need to apply some temperature gradient, means like at least 60 degree 70 degree kind of hot surface. If there is any hot surface, we have to mount on that hot surface, then only we are going to get gradient across the device. Yeah,
you studied up to 50 degrees centigrade, correct? Beyond that, what happens?
It is 50 degree
linearly?
Temperature difference, sir. But heating temperature was like 70 to 80 degrees.
Okay.
So then that is minus room temperature, then 70 minus room temperature, we are going to get about 50 degree temperature difference maximum.
Okay. According to your anticipation,
yes, sir.
What kind of impurities you are planning to add?
Usually some of the metal oxides have capability of producing higher Seebeck coefficient. Higher Seebeck coefficient producing materials are important to generate more output voltage in a small temperature gradient, like what you pointed out. With a small gradient, like even near to room temperature, if I apply just 10 degrees Celsius temperature difference, if I get better performance from the device, that would be very useful. So we are particularly interested in copper sulfide and copper oxide. Copper oxide and copper sulfide both are very good for application, but the fact is there is a decrease in electrical conductivity of the such compounds because of the addition of impurities. So we need to look what is the trade-off, what is the best possible composition to get a better output performance as compared to the pristine graphite paste.
Okay, Rafiq, thank you.
Yes, thank you very much, sir. Thank you.
One question from my side.
Yes, sir. Please.
I used a ball mill, no?
Yes, sir.
So you told for 2 days. What is the purpose of using it for 2 days?
We are just preliminarily trying, like we wanted
it for
to
mixing
get,
or size you are reducing?
No, sir. We are not worried about the size of the particles and all. We just wanted to have a uniform dispersion of graphite particles. Typically, when you take graphite powder and then just mix it with water, it is hydrophobic. So it will not mix properly, and you will not get uniform dispersion of the particles in the water. But by using ball milling, what we have observed is uniform dispersion of graphite particles in water.
What was the quantity you have taken?
It is I tried 5 gram graphite powder and about 10 ml water and about 1 to 2% of polymer PVA, and by having reaction by ball milling of 24 hours to 2 days. For 2 days, I got very nice dispersion of particles in water. When I used 1 day also, it was nice, but coatings will be better from the higher ball milled powders because dispersion will be good. Ultimately there will be a decrease in the particle size, but we are not worried about that. We are not looking into that aspect. We are only looking for a nice paste that can be coated easily on different substrates, so that we can make devices easily.
Okay, Rafiq. But there are some questions in the chat box. You can type
yes,
the
sir.
answer.
Thank you, sir. Yes, sir.
So
Yes,
what
sir.
is the main factor affecting all those things they have asked? Participants have asked the question. Huh?
Okay. Yes, sir. Thank you, sir. Thank you, sir.
So thank you, Dr. Rafiq. This was indeed a very informative talk, and thanks for making it a short presentation also.
Yeah,
so
yes.
Thank you so much. As we are running out of time, we will quickly move on to the next speaker, Dr. Mallikarjun from Karnataka University, Dharwad. Topic is investigation of structural, thermal, and mechanical properties of high filter CDSE dispersed PMMA polymer nanocomposites. Over to you, sir. Sir, you can start. Mallikarjun sir, you can start.
Good afternoon to all. First, I would like to thank organizing committee to giving me an opportunity to present my work. My title of work is investigation of structural and thermal and mechanical properties of ice pillar CDC nanoparticle doped polymer nanocomposites. So outline of my work is the first the introduction about the polymer and polymer nanocomposites and some processing of preparation of polymer nanocomposites and characterization techniques and resultant discussion of my work. So in the recent year, the polymer are very attracted and scientific and technological researchers.
Mallikarjun, sir, sorry to interrupt you in between. Your voice is very, like volume is very low. So can you speak little loudly? Yeah.
In the recent year, the polymer nanocomposites are very attractive scientific and technological researchers due to their wide application in the optoelectronic and energy conversion and energy storage applications. So the polymer is what is polymer? Polymer is a made of is a large organic compounds. It's a comprised of repeating units monomer that are currently bonded together. So what are nanocomposites? Polymer nanocomposites are material in which the nanoscopic inorganic particles about nanoscale about 10 to 100 nanometer in the least one dimension are dispersed in the organic polymer. It is drastically improve the performance of the properties of the polymer. So why polymer nanocomposites are important? The polymer nanocomposites only the pristine polymer not fulfill our objectives. So individual polymers not allowed to satisfy our needs. So such a new material we need to fabricate. So nanocomposites are able to meet diverse design requirement with a single as well as 10 to weight ratio. So what are the advantages? So what are the advantages of polymer nanocomposites? Advantages of nanocomposites that under wonder material are becoming essential part of today's material due to the advantages such as low weight, corrosion residue, strength and fast durability. So high durability is a low expensive material. So it's a lightweight, excellent resistant to corrosion, strength to relative weight, design flexibility, part consolidation, dimensional stability, radar transparent durability. There are so many advantages of polymer nanocomposites. So in graphically I showed the so many applications in polymer nanocomposites. So in our present work I used the PMMA polymer, so polymethyl methacrylate. So it is a very good polymer. P is a very transparent polymer is then glass, low cost thermoplastic polymer. It does not filter ultraviolet light. It's good weather ability and resistance to prolonged sunlight exposure. It is a high mechanical strength, high Young modulus and low elongation at break. It's a good dielectric material. So I synthesized the quantum dots CDS nanoparticles in my laboratory by simple heating and reflux method at maintain the temperature at 80 degrees Celsius. So I show some pictures. I synthesized the nanoparticles. So many applications in CDSC. So it's a very useful property. Photovoltaic applications, laser, biochemical sensor, biomedical imaging, solar cells. So many applications in CDSC nanoparticles. So it's a simple process to fabricate the polymer nanocomposite membrane. The CDSC PMA nanocomposite film were prepared with the different weight percent of CDSC. So different weight percent I doped I pillar content. So 2 weight%, 3, 4, 6, 10, 8 to 10 weight% CDSC I doped to polymer. So a prepared nanocomposite, which is a prepared polymer nanocomposite is transparent. So I characterize some analyze the structural and thermal and mechanical property of the polymer nanocomposite using the different experimental techniques. So these are the experimental techniques I have done. ATR technique and XRD and AFM, thermal analysis and mechanical properties of the polymer nanocomposite. So this is the ATR analysis. So in ATR analysis, it's a good method to study the interaction of the CDS nanoparticle in polymer matrix and identification of the functional groups. And FTR spectra, it shows the 3295, the wave number at 3209 per centimeter due to the stretching of hydroxyl group present in the polymer. Okay. So in the another peak, the broad peak is to the 2993 per centimeter and 2950 centimeters are assigned to the stretching of CS3 and CS asymmetric and symmetric band respectively. The sharp peak, it shows sharp peak. It appear at 1723 per centimeter and 1523 per centimeter assigned to the carbon and carbon double bond stretching. It is a and when we doping the CDC, the high pillar content of CDC, we dope it is a with wave number. Its intensity also increases in the we have observed from the FTR graph. So it is the XRD pattern of our polymer nanocomposites. XRD pattern is useful to study the average crystallinity size of the polymer nanocomposites. So I estimated some values of XRD pattern. So average crystallinity size is increases on doping. Okay, and calculated fluid type maximum and intercrystallinity separation of the polymer nanocomposites. So this is the thermal study of the polymer nanocomposite. So the thermal study is very important technique to for polymer nanocomposite. The stability of the polymer. It at what temperature it is at what temperature we have to maintain the polymer membrane. So we have to explain here. So in figure 3 and 3BRB shows that figure 3 is the DAC, the differential scanning calorimeter, and PGI the thermogrametric analysis graphs I plotted here. Due to the dispersion of CDS, the glass transition temperature increases from 155 degrees Celsius to 162 degrees Celsius on doping concentration of, I got to forget some correction here. The melting temperature has been increases from 270 to 340 degrees Celsius. The is the first endothermic peak. The prominent second endothermic peak at about 395 degrees Celsius to correspond to the degradation temperature. The thermogravity analysis TJ is another relevant technique to explain the thermal behavior of, and investigated the percentage of weight loss with the temperature. It is the surface morphology of the prepared polymer nanocomposite. So AFM, it is a pure PMMA. It shows the some hardness of the surface. On doping, the 2% and 10% I plotted the I captured the images. So the pure PMMA illustrated the irregular surface due to the dispersion of CDC quantum dots in PMMA. The nanocomposite shows the smoother surface morphology compared to the pure PMMA nanocomposite films are seen. So this is the mechanical study of the polymer nanocomposites. Mechanical properties. So it is a very useful technique to study the stability, mechanical strength of the polymer. I estimated some parameters, mechanical parameters such as Young's modulus and tensile strength and the percentage of elongation at break of the estimated I plotted, showed in the table. It is a for the pure PMA, it's a good Young's modulus and tensile strength, and its bracket is 5.2. It is a 2% of polymer doping CDC. It's a break suddenly, so it doesn't show the Young's modulus. The 4% CDC doped polymer shows the Young's modulus 857 megapascal. It is a mechanical property. It shows the good mechanical property of the polymer nanocomposites of the prepared polymer nanocomposites. So in our present work, given a summary, the CDS PMA nanocomposites film fabricated using the solution costing technique. It is a very simple technique to fabricate the membrane. The FTR peaks examine the complex formation between the CDS and nanoparticle dispersed in the polymer matrix. The surface morphology of the roughness of the CDS PMA are analyzed by AFM technique. The average crystallinity of the crystallinity is increases with the undoping. Okay, the DSC and the TGS so the good thermal stability of the polymer nanocomposites and also mechanical property of the CDS PME are estimated. The prepared composites exhibit the good structural, thermal, and mechanical properties. So therefore, the prepared nanocomposites films are easy processing and very flexible and very good transparent material. Find the wide application in the such as energy conversion, energy storage applications. So this is I am thankful to this author to grateful to Science and Technology Research Board and Department of Science and Technology, Government of India for research fellowship. The author to thank New Delhi for SAP CS page 2 providing the research grant. The author are thankful to UC KV Dharwad for providing the experimental facilities. This is my research research group. So Mallikarjun, Chetan, Chavan, Somya, Kanakraj, Madhavi, Suprasa, Satya, Chandrappa. So and finally, I thank to my research guide, Professor RAMAIAH, to give me to provide the all experimental facilities. Thank you to all for your attention. Hello, ma'am.
Yes, sir. Thank you, sir. Now, Professor Nagbhushan, sir, you have any questions? You can go on, sir.
Mr. Mallikarjun.
Yes, sir.
Can you hear me?
Yes, sir. Yes, sir.
Okay. First question to you is, how did you manufacture this PMC?
PMC, sir. Sir, I prepared by solution casting method, sir, in our laboratory.
Which casting? Solution casting.
Solution casting method.
Solution. How are you adding this particles? Which is the matrix and which one is the reinforcement?
Sir, polymer is the matrix, sir.
Okay.
The CDSC nanoparticle is the reinforcement.
Reinforcement. How did you add it?
So by weight percent, directly I added to polymer matrix, sir.
At what time? At what temperature?
By directly I added to different weight percent of nanoparticle to the polymer, sir. Directly I added to polymer matrix.
Okay. Go to the previous slide next to conclusion.
Yes, sir. Yes, sir.
Given the properties, no? Mechanical properties.
Yes.
Before conclusion.
Yes, sir.
Before conclusion.
Yes, sir.
Here you have mentioned the particle percentages, 2%, 4%.
Yes, sir.
Why for 2 and 6%, the Young's modulus is 0 or it has broken, whereas for the 4% there is some value.
That is my polymer membranes are very, so actually we need a 10 centimeter length for study the mechanical property for my instrument. So that is after the fabrication it is a very brittle, so you got the small scale length, so that's why that is suddenly break. It doesn't
at 2%, but what about that 6% at least? Can you see the table?
So it doesn't show, sir, 6%.
Magnify the table or full screen.
Yes, sir.
For the 6% also there is no any value.
No, sir. It doesn't show. Actually, the mental.
What may be the reason? Because from 1000 there is no for 2% you are not any value, whereas for the 4% you have got 800 MPa. Is it right? Megapascal.
Oh, yes, the 4,000
okay. Suddenly it has been once again for the 6% you have not got any value. What was the load applied?
I will go through once again for again I prepared my samples. I will go through once again for study the mechanical.
Please check it, but what is the load applied? Please have a look over it.
Okay, sir. Okay.
And also for the elongation. Elongation 5.2, it has reduced to 1.2, and then 2.7 it has been increased. Once again it is reduced. Why is this changes happening? In the case of
elongation. Yes.
You see, the values are oscillating from 1.2, 2.7, and then 1.2. What may be the reason?
Sir, actually the polymer, that is the membrane, it's varying the doping, sir. Actually, varying the doping.
Okay, please check over it.
Okay.
Okay, thank you.
Okay, Mallikarjun.
Okay.
I have some couple of questions.
Okay, sir.
Are you a researcher? You're doing PhD now?
Yes, sir. Yes.
Okay, then no problem. There will be an excuse for you. Okay. Because the paper, your presentation is totally fail.
Yes.
Because as our chairperson, Sir Siddharaju said, the whole mechanical property is not systematically studied. Okay.
Yes,
because you see, look at the first one, you are showing for the first dopant concentration, second one you are skipping,
yes, sir.
third one you are giving some value, after that disappeared, correct? Whatever may be the value,
okay,
it may be less or more, you need to give systematically presentation to be done.
Okay.
And I found that you are claiming that 10 weight percent, correct, you have added.
Yes, sir.
Yeah, your material is transparent or black?
Black, sir, black.
Black only, but you told transparent, correct?
Yes,
na?
yes, sir.
And FTR, of course, you are not a chemist man, that is different issue, but within 1000 degree, you find a lot of peaks are observed, correct?
Yes, sir.
FTIR.
Yes, sir.
You didn't written anything about that one in this one, correct?
Okay,
na?
okay.
Even a DSC analysis also you have not done properly, correct?
Okay.
And you have done the surface morphology. What is the purpose of carrying out surface morphology?
Just confirm dispersion of nanoparticle.
No. You cannot claim dispersion, okay, just by looking at your AFM, correct? Na?
Changes of the
totally
polymer matrix.
Nothing. You have to interpret your surface morphology with your mechanical property there.
Okay.
Correct? Na? All results should be one-to-one interlinking must be there. That is a good result. You have done FTR. Why you have done FTR? Correct, na?
Yes, sir.
Yeah, every result should be linked with this one. That is the exact interpretation. Anyway, okay. All the best, Mallikarjun. Fine.
Okay, thank you, sir.
Fine.
You can improve upon. There is a lots of scope for improvement. Okay. Now further you can carry out research and do well. Okay. All the best.
Okay, the next oral presentation will be given by Mr. Ganesh Sridhar Hegde from Manipal Institute of Technology, Department of Physics, on the topic enhancement in thermoelectric figure of merit of indium and selenium co-doped bismuth telluride. The time limit is 8 minutes, Mr. Ganesh. Okay?
Yes, madam.
Yeah,
Yes,
you
madam.
can start. You can start now. Over to you.
Yeah, I'll share the screen, madam.
Yeah, sure.
Sir, madam, is it visible?
Yes, it is visible. You have started sharing?
Yeah, madam.
Yeah, it is visible.
One
you can
second,
maximize
madam.
Yeah,
madam.
You can maximize your slide and you can start.
Yeah, is it visible, madam?
Yeah, correct. You can go on, sir.
Yeah, thank you, madam. Good afternoon, everyone. I am Ganesh Hegde, research scholar from the Crystal Growth Lab, Department of Physics, MIT, Mahe, Manipal. I am presenting my research work on the topic of enhancement in thermoelectric pair of merit of indium and selenium co-doped bismuth telluride. My paper code is OA03. So, due to the rise in population and due to the rise in global warming, also because of the lack of energy resources, we have to get the alternate energy resources. So that's why we have chosen the topic of the research problem like thermoelectric effect. So the thermoelectric effect refers to the phenomena by which either a temperature difference creates an electric potential or an electric potential creates a temperature difference. So in other words, when we are inserting a temperature to a certain material, there will be a production of electricity in the two dissimilar junctions. So the direction of heat of flow can be controlled by the changing the polarity of the voltage sources. So there will be some applications of the thermoelectric materials. So we can given as the thermoelectric seats of the car. Because of the body heat, that car seats acts as a thermoelectric generators. So also the waste heat generated by the industries can be caught by the thermoelectric materials and converted into electricity. And they are also used in the medical sampling coolers, like keeping the samples and blood samples, etc. The thermoelectric Peltier cooling applications will be used in these devices. Also the space probe and the radioactive isotope generators and the portable thermoelectric watches, etc. So the thermoelectric effect can be divided into two effects. One is Seebeck effect and the other is Peltier effect, where the Seebeck effect is a phenomena where the heat is applied to a material and we will get the electricity in the two dissimilar junctions. And the Peltier effect is the reverse effect of the Seebeck effect, where we can expect the incident electricity will generate the heat in the two dissimilar junctions. So these two are the interrelated effects of the our thermoelectric effect. Because if you consider a fridge, in fridge there will be two phenomena. Inside it is cold and outside it is the equal amount of heat will be liberated by the fridge. So that means it has two effects like Peltier effect and the Seebeck effect. So the applications of what material we are using is only the matters when we are doing the Seebeck effect and the Peltier effect. So we have to qualify the thermoelectric material in a proper manner. So that's why we have some quantity called thermoelectric ferromerit, which is also called dimensionless ZT. So it is formula given by S square into T by kappa into rho, where S is the Seebeck coefficient, T is the temperature applied, and kappa is the thermal conductivity, and rho is the electrical resistivity of a material. And where we have considered the total thermal conductivity as combination of phononic thermal conductivity, which is also called lattice thermal conductivity, and the electronic thermal conductivity, which is also called charge scattering thermal conductivity. So coming to the methodology. So as I earlier told that our material is based on indium and selenium co-doped bismuth telluride. So the total methodology is based on solid state reaction. So the grinding is done for 2 hours with the stoichiometric ratios of all the elements, and it is pelletization in the Phyton compression, and which is pelletized with the help of the pelletizer die set, which is a tungsten carbide, which is of dimension 5 into 10 mm. And we have vacuum sealed the sample with the help of the 12 mm quartz tube with a butane burner with a vacuum of 10⁻⁶ torr, and it is sintered in 420 degrees Celsius for 24 hours. And the samples are sintered. It is again reground to get the homogeneity in the mixture, and it is pelletized. And again same process is carried out until the furnace is until the sintering temperature at 200 degrees Celsius for 12 hours. And we have got the samples like this, which is 5 into 12 mm and 1 mm thickness of the samples pellet. So coming to the results and discussions. So XRD patterns have been taken in the range of degree of 20 degree to 80 degree with a step size to 0.02 with a rate of 2 degree per minute. So where we have obtained 0.15 peak, if you can see here, 0.15 peak is the highest oriented peak among all the samples, which shows that the sample has monotonic phase structure. And whenever you dope Se0.3 into the matrix of bismuth telluride, there is a slight shifting in the XRD peak patterns. Also, when we are dope indium 0.02, indium 0.04, there is also some small shift in the higher 2 theta angle order side, and hence we can conclude it as the above phenomena may be because of the could be because of the difference between the ionic radii of the dopant atom and the parent atoms. For example, Bi is having the larger ionic radius and the indium is having the smaller ionic radius. In the same way, tellurium and selenium. So that's why we have got the lattice strain in the increasing order. So which shows that there is an increase in the strain and there is a decrease in the lattice parameter, and the crystallite size is calculated by the Shearer formula, which is decreasing gradually with the dopant concentration and the dopant elements. So we can conclude it as our crystal is a totally compressive nature of the crystal, which shows that there is a contraction. Hence, to know the calculated and observed XRD peak patterns, we have performed the right field analysis, which is shown in the figure 3. So hence, we have got the RP value, RWP value, REP value, chi-square value, which evaluate the fittings of the XRD peak patterns, which is done by the Expo 2014 software. So coming to the field emission scanning electron microscopy, which shows that surface morphological behavior of our polycrystalline samples. So the sample Ba2TE3 is having some kind of more porosities, which is due to the volatilization of tellurium compound. And again, when we dope in the selenium in the matrix of bismuth telluride and indium in the place of bismuth and indium 0.04 in the place of bismuth, we have got some reduction in the some slight quantity of porosity behavior, which is partially due to the subduing volatilization of selenium. There are some irregular grown grains above the sizes we can observe, not like nanoparticles. It's the polycrystalline material as we know it. So above surfaces are due to the severe TESC vacancies. So the volatilization of selenium is observed in some areas due to its, as we know that it has a high vapor pressure. So coming to the thermal conductivity and electrical resistivity. So first I will explain about the electrical resistivity. That is our highest electrical resistivity is experienced by the sample indium 0.02 and the lowest electrical resistivity is experienced by the sample indium 0.04, and the moderate level of electrical resistivity is obtained by the rest of the samples. We can know that there is some when we dope indium into the matrix of bismuth telluride, there are some anti-set defect formation. These anti-set defect formation acts as electron generating centers, and because of these electron generating centers, there will be variation in the electrical resistivity, and we have obtained the lowest electrical resistivity for the indium doped with 0.04, which is because of the probability of bond formation between bismuth and tellurium is less when compared to the indium and tellurium, and the bismuth selenium is less when compared to the indium and selenium. So indium acts as an anti-set defect generator. So this will act as a potential candidate for our doping material. And also when we are talking with the thermal conductivity, the highest thermal conductivity is obtained by the pristine sample, which is shown in the black color Ba2TE3, and the lowest thermal conductivity is obtained by the sample indium doped with 0.02, which is the highest thermal conductivity is mainly due to the short mean free path of the sample, which doesn't have any anti-set defect, and the point defect. When we dope indium into the matrix of bismuth telluride, there will be some anti-set defect will be formed. Also, it's a point defect. This point defect also acts as a electron scattering centers. These electron scattering centers acts a phonon-phonon interaction, and here beyond the 200 range there is a phonon-electron interaction. So because of all these phenomena, we have reduced the thermal conductivity due to the co-doping. As our title only says that it's a co-doping. So we have achieved the co-doping optimized thermal conductivity in our sample indium 0.02. So coming to the Seebeck coefficient, power factor, and the ZT values. Seebeck coefficient is highest in the sample, which is again we have doped in the sample indium 0.02, and the least in the sample doped with selenium, doped with bismuth telluride. So the highest Seebeck coefficient is mainly due to the doping of indium, which shows that there is a fifth donor electron atom, and this donor electron acts as a mover, and hence we have got the samples like N-type behavior. Also, we can conclude that there is a donor-like effect is produced when we dope indium and selenium into the matrix of bismuth telluride, as there is a vacancy of TESC, which will produce the increase in the carrier scattering, and which increases the Seebeck coefficient phenomena. Also, when we are calculating the power factor, it's a formula calculated by S square divided by rho. Means S is Seebeck coefficient and rho is the electrical resistivity. So we have got highest power factor for a material. Again, the indium doped with 0.02, which is a co-doped sample. Again, there is no difference between the indium doped with 0.04 and indium doped with 0.02, which is because of the significant reduction in the electrical resistivity as well as significant change in the Seebeck coefficient, as it is a derived quantity among the measurements of a power factor. So again, if we consider ZT of a material, we have got the highest ZT among the, again, indium 0.02 sample is the highest doped sample, highest ZT sample, and the least is obtained by the selenium doped sample, which is doped with bismuth telluride. So which is because of the significant reduction in electrical resistivity and significant variation in the thermal conductivity, and also the variation in the Seebeck coefficient. As I have already told you in the formula, that is S square into T by kappa into rho, is a formula which is used to calculate the ZT value. So by this all this effect, we can conclude that we have got the ZT value of Ba2TE3 is 0.12 at 350 Kelvin, and co-doped with indium X is equal to 0.02 at and has shown the ZT of 0.6 at 350 Kelvin, which is about 5 times greater than that of the pristine sample, and we have achieved the co-doping optimization through this research work. So high ZT values of Bi 0.98, indium 0.02, twice T 2.7, Se 0.3 could be, or it can be used for near room temperature Peltier cooling applications. So coming to the acknowledgement, I thank my university, Manipal Academy of Higher Education, for helping my in this research by giving the fellowship TMAPI under Dr. TMAPI scholarship scheme. And I thank my research supervisor, Dr. Ashwata Narayana Prabhu, and I thank my collaborator, Dr. Ashok Rao and Dr. PD Babu. And I also thank my senior Vinay PP and Ms. Rhea Thomas, Mr. Suraj Gangavati, Mr. Guru Krishna K, Mr. Manoj SP, and Mr. Pawan Acharya, and all the research scholars of the department. So these are all the references which I have referred till now. Thank you, madam. Thank you, sir.
Okay. Ganesh.
Yes, sir.
Yeah, your work is good actually. You have done a lot of
Thank you, sir.
work actually.
Yes, sir.
In your compound, you fixed selenium 0.3, correct?
Yes, sir.
How do you fix 0.3?
Sir, in literature survey, when I was doing literature survey,
You have
so there
taken
was
0.3.
yes, sir. The 0.3 SE is having the highest ZT value.
Okay, okay,
So I can consider as a literature as a base material for our research work. So I could say that reason. So selenium will be 0.3.
Yeah, that bismuth telluride is well studied thermoelectric material, correct?
Yes, sir. Yes, sir.
According to literature survey, what is the novelty you are claiming here?
Sir, in our research, the co-doping has not been done so far, as per my knowledge. So the co-doping may vary the latest parameters in a drastic manner. So we have controlled it in our research. So we have found out the repeatability in this research work. So co-doping is a novelty in the low temperature, especially low temperature range of thermoelectrics.
Okay, how do you compare your material with other well-known thermoelectric materials?
Sir, I can consider Bi2Se3 as a compatible material for Bi2Ta3 in the low temperature only. So other material is PBT, as our one of the presenter has told that PBT is one of the material, but it is good for high temperature, as per my knowledge. And Bi2Se3, Bi2Ta3, indium selenium is a costly material, and indium telluride is again the costly material, and also germanium telluride is there. It is also costly material. So the affording cost effective, which according to my concern, is bismuth telluride, bismuth selenide are the compatible material according to me.
Okay, okay.
Ganesh Shegde,
yes, sir.
Is there any relation between the porosity and thermal conductivity?
Yes, sir. Yes, sir. Yes, sir.
How it is connected?
Sir, we are using selenium and tellurium in the compound. So whenever you sinter the compound in that 400 degrees Celsius in the first sintering, and there are some densification of the compounds, and also there is some volatilization of selenium, which causes the scattering of the electrons, variation in the scattering of the electrons. This scattering of the electrons may affect, will affect the thermal conductivity in a proper manner. Means if bismuth telluride is having the highest thermal conductivity, it doesn't have selenium. When we add selenium into the matrix or bismuth telluride, it has some reduction in the thermal conductivity. That means there is some TESC vacancies and a TESC porosity, which acts as a scattering centers for the electrons. This will make the long mean free path for the electrons to travel more length. So there will be some easy path for the electrons. So this will cause lowest electrical thermal conductivity in our co-doped samples.
Okay, all the best.
Yes, sir. Thank you, sir. Thank you, sir.
So thank you, Ganesh.
Yes,
all
ma'am.
the very best for your work. Right?
Should I stop the sharing, madam?
Yeah, you can.
Yeah, thank you, madam. Thank you.
Yeah. So we will go on to the next oral and the last oral presentation for the day by Mr. Sharath. Presentation number OA04, Growth and Optoelectronic Properties of Semiconductor Nanocrystals. Right? Over to you, Mr. Sharath.
Madam. Thank you, madam. So, madam, PPT is visible, madam? Hello?
Yes, sir. Yes, sir.
Okay. So, hello everyone. So, I am Sharath, so research scholar, Department of Physics, Davangere University, Davangere. I feel very privileged to be participating in IQAC. So, I am here to share a few aspects about the growth and optoelectronic property of a semiconductor nanocrystals. So let's start with the introduction of the topic. So nanotechnology is an application to produce devices and products. Nextly, we'll go for the nanoscience. So nanoscience is the study of the nanomaterials, their properties and phenomena. So the rough definition of the nanoscience could be at least one dimension less than 100 nanometers. Nano derived from Greek word nano means draft or a small. So nano is 10 to the power of -9 or a 1 millionth in its size. So here we can observe this diagram. So nowadays the standard scene is reduced to the nano size for the utilization. So the famous Richard Feynman said that in 1959 intimated there is a plenty of rooms at the bottom, so manipulating the atoms and molecules directly. So 1/10 scale machine to help to develop the next generation of 1/100 scale machine, and so far. Semiconductor nanocrystals plays a very important virtual roles in the modern technology applications because of their size-dependent optical and electronic properties. Nanomaterials exhibits a high size, shape dependent physical and optical properties of a possible applications, and maintains the batteries, converting the devices catalyst, chemical and biological sensors. Achieving the fine-tunable of optoelectronic properties, the colloidal nanocrystals, one of the main focus of the research nanoscience and engineering. The critical radius of the nanostructure can be vary from 2 to 60 nanometers, or depending upon their identical groups like 4, 3rd and 5, 2nd and 6, or 4 and 6. The size an important role for in the optoelectronic properties of a semiconductor nanocrystals. We can take it as a quantum dots. So the quantum dots are nanocrystals defined as a crystal semiconductors which has nanometers in a diameter, typically containing only a 10 to the power of 2 and 10 to the power of 4 atoms. So when we reduce a bulk material or a macro size to the nano size, we will get a nanocrystal semiconductor. So when the size of the semiconductor nanomaterials decrease, the level of the electrons and excitations to the plane, the physical boundaries. So physical boundaries of the particles, the material starts to adjust the energy levels in the response of the changing in the size, and thus exhibits a phenomenon we known as a quantum confinement effect. So the main importance to study these concepts, the importance of the surface atoms, that is the large density, highly reactive and more surface energy changing in the chemical, optical, mechanical, magnetic and thermodynamical properties. Surface atom can be obtained by the organic molecules. So where we compare with the golden nanoparticles, while changing with the results of the applying the capping of molecules. So why to study the optoelectronic semiconductor nanocrystals compared to the bulk materials? Optoelectronic semiconductor nanocrystal cost less, weigh less, having less attention and dispersion, and provides a more band gap. Optoelectronics is the study of the application of an electronic device and the system to detect and control the light, usually considered a subfield of a photonics. So optoelectronic devices are opto to electrical or electrical to optical transcenders are instruments that such a device in their operations. Optoelectronics is based on the quantum mechanical effects or light on the electronic materials, especially in a semiconductor. So the light interaction of the electrons we can take for the applications. As the global technology revolution necessity, the research for new materials more efficiently devised in the electrons and semiconductor industries. Wide range applications of the application for the elements in group 16 of the periodic table, such as sulfur, selenium and tellurium, so are expected improvements to execute the existing technology. For last 2 decades, there has been terminated the interest in the metal chalcogenates nanocrystals, knowing to their unique optical properties, and these properties distinguish the nanocrystal chalcogenate from bulk structure. So now we are planning for the experimental section of the experimental section. In this section, the band gap energy of a nanocrystalline chalcogenates of group 2 or 6 or group 4 and 6 among the different nanostructured chalcogenates like lead, zinc, with comparing with these selenium, titanium, tellurium, so cadmium and Ag2, and their core shell formulation are of significant importance. Silver chalcodonate, which has in low toxicity and narrow band gap of the range 0.9 electron volts for bulk Ag2s, 0.15 electron volts for Ag2Se, and 0.67 electron volts for Ag2Te. Their synthesis, the process is relatively easier and they can be used to prepare a high quality nanocrystals in terms of size and shape. According to the solvent used in the synthesis of the semiconductor, Ag2Se quantum dots were synthesized in an aqueous solution at room temperature. So particle size is tuned by controlling the reaction time and temperature. The characteristics we are planning to study XRD, FTIR, UV, so photoluminescence, TEM, and impedance measurement. So motivation of the future work to prepare a size tunable Ag2Se quantum dots, capping these suitable organic molecules to create a monodisciplinary and stable colloids, development of the low cost electronic device based on a Ag2Se quantum dots. Future application of the optoelectronic semiconductor nanocrystals are minimizing the size, faster speed and operating, integrated photonics, integrated circuits using a waveguides for the interconnections between the devices. So applications, infrared remote controlling devices, smoke detectors, astronomical, military security purpose, so night vision equipments, biomedicals, X-ray image, electrochemical sensors, data storing device, photovoltaic and IR detectors, the rationable for these users, the future scope of their applications. So I thank you all for giving this opportunity for the organizers and my guide, MN Kalsat sir. Thank you.
Sharath, do you? Okay. Sharath?
Sir?
Are you beginner?
Yes, sir.
Okay.
I'm the beginner. I'm working from one.
You have done some review article,
Yes, sir.
You're doing some research. Okay, fine. Okay. Because your work shows there is no experimental presentation
Yes,
here.
sir. We are planning for the experimental. Due to the COVID, we can't do the experimental.
I can agree with you. But later on in the future studies, you are concentrating on silver selenide, correct? Ag2Se.
Sir, yes, Ag2Se.
Future study. Why can't you go for other, for like lead selenide or zinc selenide or cadmium selenide? Why? What makes you to work only on Ag2Se?
Sorry, because we are using a simple chemical method, sir.
That is fine. But your return, I think you might have selected 4 samples, correct? Now, lead, zinc, cadmium, along with the 16th group elements, correct? Na?
Sir.
Like sulfur, selenium, and telluride, correct?
Sir.
Among those, you you are given some little more information on silver selenide, Ag2Se.
Ag2Se, depending upon the bandwidth.
Okay. Why you are concentrating only on this particular material?
Sir, because it is very workful for the future application, sir.
Then other one is quantum dots. How do you prepare quantum dots? Are you preparing?
Sir, no, sir. Just to your plan.
No. Yeah, you are planning. How do you prepare? You don't have any plan at present.
No, sir. At present.
Okay, beginner. Okay. Start Madilam.
Sir.
So not started work actually.
No, sir. Still we are planning, sir.
But I could not see references. Have you gone through complete literature survey? In your slide, where it's mentioned.
Yes, sir.
How many papers did you refer?
So up to still I prepared about 455 papers.
But reference section I could not find, or any you are not quoted anywhere.
Yes, I can quote.
Because COVID will not restrict you from reading. Correct now?
Okay.
Nowhere you are mentioned.
Yes.
Correct now? When you go for a paper presentation like this, you should mention about the reference, citation, all this. Okay, thank you.
Heartily thank you for the answer.
Okay.
The best presenter is
Okay, thank you, Sharad.
Thank you, madam.
So we are done for the day.
I want all the
participants to log in tomorrow. 15 minutes before, that is around 9:45, our session will start from 10 o'clock. Same Zoom link you can use. For your convenience, the Zoom link will be again given to you through WhatsApp and email. Okay?
Okay.
Thank you so much. So the feedback link will be sent again to the email itself. Right? Those who have not received it, they will receive it in the email link also.